Okay, we're gonna start in a couple of minutes. Okay, we are just waiting for people to come down from the coffee break, and we're gonna start. Okay. Yeah. Good. Hey. Oh. Okay. Hi, everybody. Thank you for joining us for BeNeRL 2026. So it's our pleasure to have you here in our MindLabs building. So this is the building. Just a little forward. This building is a part of a collaboration between Tilburg University and other local knowledge institutions with a lot of objectives, both in teaching, research, and business development. For Tilburg University, we mostly use MindLabs because it hosts 4 laboratories from my department. They are all 4 rooms around this room here. And it also hosts my lab that I share with my colleague Murat Kirtai. My lab is actually that room over there, so please let me know if you want to have a little tour or have a look around. We will try to show a few simple robots during the day just for fun, because that's more of my research topic. About BeNeRL per se, this year I've been organizing with my colleague Maria Popovic. Here, there. So it's always fun to organize these kind of events. Quite a bit of stress, but I hope you will enjoy it. We do have an exceptional catering, especially for lunch. You're going to see we're going to have some very good food. We want to thank our sponsors. So this event is made possible by NWO Scientific Consultations and Meetings grant. Tilburg University that co-sponsored the event, and MindLabs, which can very kindly offer the facilities, the very professional live streaming and video editing at the end of the event. So we are very, very thankful for them. We also want to thank our volunteers. So we have an army of student volunteers. You can find them around with the blue ribbon and an orange tag. So if you have any question, either ask me or ask them. We have a WhatsApp group, so they will let me know of any issue or of any question that they cannot answer. So do ask around. And of course, thank you for the participants. Of course, this event would not be possible without this large community of reinforcement learning researchers in the area. Now, I want to keep this opening short, also because we have a very tight schedule today. Just want to give some statistics because we are scientists, so we always like statistics. BeNeRL is as most of you know, is the premier workshop for reinforcement learning researchers in Belgium and Netherlands. So it is nice to show that actually attendance is mostly Belgium and Netherlands, but we do have attendees from neighboring countries, which is very nice, including 2 of our speakers who are coming from Germany today. Composition, this pretty much I think what could be expected. It is mostly PhD student and some faculty, but we do have some industry and otherwise participation, so that's always nice to have. Schedule, I put here as a summary, but you can find it on the website. We have a very intense morning session with 4 talks and a coffee break and lunch. And the afternoon session with the last 2 talks and the panel discussion. The afternoon session, we might want to rearrange something around depending on time, but we hope to be able to stick to the schedule. And that's it. So without further ado, let me start by introducing our first speaker, Mariam Tavakol. Mariam is an assistant professor at the Uncertainty in AI group at TU Eindhoven. And today she's going to talk about reliable model-based offline reinforcement learning. So please join me in welcoming Mariam in the first talk.
Thanks for the introduction. Good morning, everyone. My name is Mariam Tawakol, and in this talk, I'm going to talk about model-based offline reinforcement learning and how we are going to build more reliable models that can be used in this kind of scenarios. Thanks for the introduction. Good morning, everyone. My name is Mariam Tawakol, and in this talk, I'm going to Okay, so how I use this one. So we are all from the RL community, and we are aware and kind of proud of a lot of success that RL had in this many tasks, from games to like robotics to autonomous driving and so on. So a key aspect in this kind of task is that we are able to do online interaction with these environments and gather feedback, receive feedback in return, and like improve the models via this interaction and trial and error. But this is a luxury that we don't always have in many real-world problems, right? So if you're talking about data-driven scenarios, like even if they are high-stake tasks, like the healthcare, so it's not something easy that we can like interact with the patients to like gather data and say, okay, let's try this medication or this treatment and see what happens, right? So in these scenarios, maybe we have large historical data available that are logged from previous treatments or interactions, but there's no possibility to do active data collection or interaction. It might be impossible or very costly in some tasks, like if you're talking like big e-commerce websites, or it can be dangerous, like in this healthcare example. There are also, for many tasks that we can design simulators, this is also not very practical, or maybe it's not very straightforward to do so, or even like they might not exactly match the real world scenarios. So the people working on robotics maybe know that better. This brings us to like the offline RL research that began to address this kind of problem. So in online scenarios, usually we have this interactive way of a model working with the environment or with the world to gather data and update its internal policy. As opposed to that, we have now offline RL research that the data is already collected from the world that is offline now, and like the other standard machine learning methods, like supervised learning methods, we are dealing with a model that is only interacting with this fixed data set, which might not be ideal. So the data that we have is in the form of like state, action, reward, and the next state. And then the goal of offline RL research is to leverage this offline data set to build models for cases in real world that the simulation or interaction is not an option. But the main challenge in offline reinforcement learning is the distribution shift. So when we have a data set that is collected from previous collection from a different behavior policy, we don't have, usually this data is not with a good coverage or good quality that we can reuse for the whole tasks. That if it was, we could just use imitation learning or behavior cloning to learn from that data. But because that's not the case for many applications that we have, what can happen is that if we just employ the existing RL algorithms that are there on this offline data set without new interaction, the extrapolation error can happen. So as we move away from the support of the data, and even if we have longer horizons, then this distribution shift becomes larger and larger, and the extrapolation error becomes also greater. So therefore, this is the problem that we have, because the data set that we use for training and for deployment, there is a shift in there, and therefore we need some new approaches for addressing RL tasks in these problems. So therefore, offline RL research started with model-free methods. That was maybe the most straightforward way of handling those. So there are a class of methods that are based on policy-constrained methods to learn policies that are constrained to stay close to data by penalizing out-of-distribution trajectories, so to do the constraint optimization during policy learning and enforcing this conservative. But there are also a class of conservative methods that directly focus on like the value functions or the reward function to avoid overestimating the values in the uncertain area or out of distribution area. So the main problem with model-free methods are that we don't have a model, of course, and then what we can do, we can have policies to generate new actions, but we can't go beyond the states that we observed in the data. That naturally motivates the use of model-based offline RL methods, that in there we can learn reliable empirical MDPs, like a dynamics model from the data, and then use it for during the policy learning, like it can handle, for example, the counterfactual reasoning, or we can even have the models and use it just for the planning. And the models can naturally be used for generating new trajectories, and that can be used for augmenting the data set and improves sample efficiency and coverage. And potentially, when we have the models, and also maybe we can use it for cross-domain generalization, or when we have some more shift across domains, and then it might be more useful. That I will also talk about that today. But the problem is that we still don't have a good quality data. So how we can learn a good dynamics model from the data that doesn't have a good coverage on the environment that we are going to address? So the main problem or the challenge in offline model-based offline RL becomes how to have a reliable offline world model, right? So how we can trust the model beyond the data that we have. So we already have a data that in the blue area, and then as we move away from this support of the data, we can go into very uncertain area that any arbitrary behavior can happen from the model and later from the policy. Therefore, this is something that we want to avoid. So there are two ways to look at it. One is that if we know where not to trust the model, so if there is a way that we know, okay, so there is safe, there is not safe. So to do that, we can estimate the epistemic uncertainty of the dynamics model and use it to avoid or identify these OD trajectories and either stop learning there or be more cautious when we learn there. And the other direction is that we don't just want to know what is safe to do and what is not safe to do, but also we want to generalize beyond that, like how we can create new trajectories or new behavior beyond this data that we have without going into unsafe exploration. So let's start with uncertainty estimation. So a lot of research in model-based offline RL has been done for uncertainty estimation. Many methods use heuristic ways to estimate the uncertainty of the dynamics model that we learn, and then use that value of uncertainty to constrain the optimization, either explicitly, by penalizing the reward, or implicitly during the optimization. And one way that works, one common approach that works a lot in practice is using the ensemble models, just to learn an ensemble of models for dynamics model, and then just use the disagreement between the ensembles, so for example, the variance or the standard deviation of the predictions to measure the uncertainty for a given state and action. So this works fine in practice. However, as I said, this is a heavily empirical approach with heuristic for uncertainty estimation, and the methods that use that is usually on the benchmark data set that are very sensitive to this hyperparameter tuning, and we don't have yet a guarantee that this uncertainty estimate from ensemble or other methods can actually upper bound the true model error. That brings us to learning or developing an admissible error estimator. So how we can build or obtain uncertainty estimators with theoretical guarantee that we can say that this already upper bounds the model error or the error in the eventual learning. Because the goal is that we want to eventually control the value errors that are induced by the model errors, right, in the policy optimization part. So what we want to do, if we have an uncertainty estimation that can upper bound this model error, and that already upper bounds the value error, then we can say we have an admissible error estimator. So there are certain simplifying assumptions in the literature that can say how we can develop these theoretical bounds. For example, if we assume that the value functions belong to the class of von Lipschitz functions and the transitions are deterministic, then this error can relate to the difference of the true dynamic and the learned dynamics prediction. And then if you have an uncertainty estimation U of SNA that with high probability upper bounds this error, then that would be an admissible error estimate. So to do that, we propose an approach to be able to estimate this bound. The first ingredient is that we use the neural tangent kernel method approach. That is a way to study the wide neural networks, so makes the neural networks that we use for learning, for example, dynamics model, wide with a small learning rate, that they can be as kernel methods. And in this way, we can analytically analyze the networks in a more tractable way. And then leverage the NTK-induced these norms from RKHS space as a measure of the learned model complexity. And by doing so, we can now turn the ensemble disagreement that we already have, for example, is the standard deviation for every state and action, and we develop a pack correction estimate of beta using this regime, and obtain an admissible error estimator U, which is scaling this standard deviation from the ensemble, like this disagreement from the ensemble. So this is what we are going to do. And for that, we first start by training the dynamics model as an ensemble model still. But this, each model is learned in this NTK regime. And then use the ensemble disagreement to estimate the model uncertainty together with this RKHS complexity correction to build this coefficient or the scale or calibration factor that is used for correcting this standard deviation to be an admissible error estimate. We further reduce the conservatism because originally this error depends on all the errors that happens in general in the model learning. But we also do a partitioning on the state action space to have a local bound that is dedicated to every state and action pair. And this error, therefore, depends on the kernel complexity and the data coverage to give how much uncertain our estimation or the model estimation on that area. So finally, we can use this error to penalize model-generated rollout in other methods, like how it is used in the literature. So this is the approach that we are presenting, but then the empirical study is still in progress. Probably in the next few months, we can talk about those. But this is how we want to have reliable models. Like we know by, for example, estimating the uncertainty, and we know where to trust the model and where not to. While this is safe and makes our learning more reliable by avoiding uncertain regions, but it might be overly conservative. And it also makes it difficult to discover new behavior or even to generalize or transfer across domains, right? So we wanted to have safety and generalization. So how we can generalize beyond the data without relying only on the uncertainty, or entirely without relying on uncertainty. So what we are proposing is to focus on cross-domain generalization and learn to connect trajectory fragments using a reverse dynamics model. So to start, I want to say what do we mean with cross-domain generalization. So more specifically, we are talking about the problems, that the task is the same. So it's like this hopper task is just hopping forward. And then we want to have generalization across environments when there is varying transition dynamics, the reward function, or initial states. So this changes the environment or the domain. So in principle, we would need new training for using the same RL algorithm to solve the task in a different domain. So why this task is important? Because there are many RL algorithms developed for single-tone environments, so that's they don't consider this change in the domains, which is in contradiction with our real world. And while there are research done on cross-domain generalization in RL, the intersection of cross-domain generalization and offline RL is also relatively new. So it's like dealing with two different problems. So what we are proposing is that we are going to learn a reverse dynamics model, either in addition to or instead of the existing or the forward standard dynamics model that we have. In the forward case, we are interested in the prediction of the next state given the current state and action. And in the backward dynamic or the reverse dynamics, we are instead the reverse prediction. Like what is the probability of the previous state given the next state and action? So what we are going to use, we adopt an existing model which is called ROMI. It's a reverse offline model-based imagination, which is used to generate rollouts leading to the goal state in offline data in a safe way. So what is it doing is like if you have something like this simple navigation task and we have the data in the blue area that is like only the data fragments that we have from this task. But as you can see, there is no information available about the big obstacle in between. So if we just use the normal dynamics model, it can incorrectly extrapolate this red arrow, which is like a forward imagination from the data, and then that is something that's not correct for our environment. And what we can do with the reverse dynamic model is like with the stitching behavior, so we move backward from the goal state, and every time that we are moving from one area from the other, that we don't have the transition available, we can predict that from the data using backward dynamics. And this provides a better way to augment the data from the trajectories that we already have. So then we propose an approach called CARI, which is a context-aware reverse imagination, which adopts ROMI for cross-domain generalization. So to do that, it already uses the model-based reverse imagination that we've seen, and it combines with a model-free policy optimization. And in addition, we incorporate context awareness, so we learn an additional context latent factor for the cross-domain generalization to make sure that it can work when changing the domains. And then we use this model to generate diverse model-based rollout to augment the data, that it eventually helps to generate more data and enable conservative generalization across domains. So we don't need uncertainty estimation here, and we don't need like unsafe exploration. We use the data that we have to generate new safe trajectories. So the overall framework is that we have a dynamics model component which learns this context-aware dynamics, and then it's used in the rollout policy to generate diverse rollouts. The output of it is the augmented data that we can create for the policy learning part. So going into each component, the context-aware dynamics model is like we learn the reverse dynamics, like we are interested in the previous state and the reward given the next state and the action. And then in addition, we learn domain-specific information in the latent vector C, which is learned for every domain. And then we use this to the reverse transition, therefore, and the reward function are learned conditioned on this latent vector of the context. And then we just use maximum likelihood and other similar methods can be used to optimize this dynamics model. And then in the rollout policy, We use a conditional variational autoencoder for this generative part to generative reverse rollouts. We start from the diverse reverse actions that are existing in the original data, and we learn a generative model that is represented by G that's generating this reverse action from the possible next states that we have in the data. Once we learn these reverse rollouts, we use this model G to generate new action and use it to in the reverse dynamics model to generate reverse trajectories, and we use them as the data from the model, which is combined with the data that we originally had from the environment to have a combined data set that is used for policy learning. Here again, we can use any model-free algorithm to learn the policy from the data set that is augmented by the reverse dynamics model. So for the experiments, we use a D4RL benchmark data set, and that's a task for Mujuku environment. So we pick two tasks, the Hopper and the Walker 2D. And there are the training task, the data is collected using 4 different types of behavior policy: random, medium replay, and medium expert, which leads to 8 total setups. And there is also a modified data set for this chaos domain generalization. The training is done on this modified data set, and the testing is conducted on the original D4RL data. And for the model-free policy optimization, we use BCQ, batch constraint Q-learning, which is already a model-free offline RL algorithm. And for the baselines, we use 3 state-of-the-art model-based methods that already incorporate reverse dynamics model, but they are not used for cross-domain generalization. So one is ROMI that I introduced already, and there are 2 other, BeNeRL and CABI. And then there is also a specific method developed for cross-domain generalization in offline RL setups, which is called DARA. And these form the baselines for our approach. And for evaluation measure, we follow the same scores from the literature of this data set, D4RL benchmark data set, which the results are averaged over 5 runs, including the standard deviation. So here is the overall performance on both tasks and 4 different data sets on each. And as you can see, our approach query can outperform these baselines in most data sets. So it's closer to ROMI because it already uses this reverse imagination from that part. So DARA is not working very good, but the methods that are based on reverse dynamics model already improve the cross-domain generalization task, and our context awareness can improve this problem further in the cross-domain generalization scenarios. So this was what I wanted to talk about. So offline RL in general is very effective for real-world problem that we are dealing with, and but model-based methods can improve sample efficiency and are better suited for these offline scenarios, but still they are highly dependent on the quality of the uncertainty estimation. But if we have admissible error bounds, we can have a better or principled way of like bounding or upper bounding these errors to have a guarantee that this uncertainty gives a true estimate of the error. But the key objective is that we are interested in balancing the conservatism and generalization. So we want to be safe, but also we want to generalize beyond that. And for cross-domain generalization, we introduced an approach called CARI, which is a novel model-based approach using reverse dynamics model and also context awareness, which showed a strong performance against existing baselines and on the D4RL benchmark data set. So thank you very much for your attention. If you have any question, I would be happy to answer.
For a few questions. So,
yeah.
So on the picture with the maze, this state space, are there any kind of requirements for your representation for this to work? Like, I can imagine that the representation that a model learns is not so Euclidean.
So if we are going with the normal forward imagination, it's possible that it's like based on distance maybe, it can predict like this, for example, these movements, it could be a trajectory that goes in the wrong direction. So here we don't use any distance awareness or something for like constraining the model how to be learned or something. So it's just learning the backward dynamics. So if there exists something like this, some gaps between the data set that we already have, so this is what we are going to learn. So there's no other things involved, if that's your question. Yeah.
I would give the microphone to the next person who wants to ask a question for the online audience as well. Yeah, great. Yeah, so any other questions?
Yeah, for the first part with the uncertainty estimation, I was wondering, do you have any intuition about how tight it is? Is it very useful, or is it an upper bound that might be quite high above the actual value error?
At the moment, it's still a bit too large for the upper bound. So it's too conservative. So if we use it, it's like it's bounding almost many transitions that we have out of the data support. So that's why we did this partitioning to make it a bit localized. But there are some more work we are doing to make it a bit tighter. Yeah, and the assumptions are a bit strong to have this. So the assumption with the deterministic transition can be extended to non-deterministic ones, but the other one is still should be there. Yeah. So.
Yeah. We have time for a few more questions. One more. All right, so thanks again, Mariam. It was a very interesting talk. All right, so I would like to invite our next speaker, Carlo De Ramo, who traveled all the way from Germany specifically for our workshop here today. Our international guest. Carlo is a professor of RL and computational decision making at the Julius Maximilians University Würzburg. Previously, he worked as a postdoctoral researcher at TU Darmstadt, and his research is all about how agents can autonomously acquire expert skills in complex real-world settings. So the floor is yours, and we're looking very much forward to your talk.
Thank you for the nice introduction. So I will see if this works. Great. And if my laser pointer can be seen by you, I guess. It's not, right? Okay. So, okay, there are some equations in the presentation. I will simply use the pointer here, which I hope you can see. Yes, great. Let me maybe laser pointer. Okay, we will do it like that. Hi, everybody. So today I want to present you our research direction on how to go beyond one-step Bellman operator. And first of all, I want to explain you what I mean by that. So let's start by seeing this graphical representation of the function space, the Q function space. This space will give us all the Q functions we can get by a parameterization theta. So you can imagine all this green landscape in front of you containing a Q function that you can parameterize with the vector theta. What we do in reinforcement learning usually is to try to find the optimal Q function Q star. This Q function Q star will most likely be outside of the function space. So we can only hope, is the microphone working, by the way? Okay. We can only hope to find the closest Q function within the function space. which is the one minimizing the distance between the real Q function Q star and the one in the function space. What we do normally is to start with a Q0, randomly initialized with parameters theta 0, and what we do is to proceed gradually by updating the Q function to go to Q theta 1, and then gradually to reach a Q theta k. And then we can still hope to go farther and farther. So this is what we do normally in reinforcement learning wherever there are Q functions involved, okay? I omitted an important step here, which is the projection step. So let's see it more accurately in this slide. We start, as I said, from Q theta 0, and what we do, in particular, to do one step to update the Q function is to apply the Bellman operator, which you can see in this slide in gamma star. So this brings us most likely outside of the function space, so we need an important projection step that brings us back to the function space. This is done by the QN, soft actor critic, DDPG, all kind of methods with critic involved, by minimizing a loss, which is the difference between the value of the target gamma star Q theta 0 and our function we are trying to find, which is in this case Q theta 1. And we proceed step by step like this. So this step is crucial and really determines how well our algorithm is going to work. And this loss, for example, is the one that the QN uses. There can be different variants, but usually it always looks like this. We have the target on the left side, so the gamma star Q theta 0 and our function Q theta 1. This loss, it's something I hope it's quite well known by everybody, but maybe it's not so well known that it's playing an important role in a very essential bound for approximate value iteration. This bound is the one from Amir Masood Faramand, found in 2011. It's basically upper bounding the convergence speed of our algorithm for finding the optimal Q function. As you can see on the left side of the inequality here, we have the difference between Q star, so the real Q function we are trying to find, and the Q function after n steps of updates. So this complex quantity here on the right side, I will, for the sake of simplicity, omit the meaning of all these complex components and focus only on the rectangle that you can see on the right side. If you, by a quick look, you can see that this quantity is exactly the approximation error you can see in this loss. So the important takeaway from this bound is that this approximation error, it's not only the one corresponding to one step, but the one corresponding to all the steps we have done from the initial step till the end step of update. So the upper bound is higher or smaller depending on how good our approximation errors have been while learning. So the takeaway that we can get from this is that a low approximation error that we get in multiple updates will give us a faster convergence. So our question that we try to address by this observation is that it would be nice to try to minimize all these approximation errors as much as possible. And in particular, if you think about the QN, SAC, DDPG, and so on, you can understand that they are all updating the approximation error step by step. So every update that you do of your Q function only focuses on one step in your sequence of n steps. So the question we ask is, can we do something more than this? In particular, can we optimize multiple approximation errors at the same time? And the series of works I'm going to present you today will all try to do something in this direction. So just to quickly summarize, we want to optimize all the approximation errors at once, or at least as many as we can. So we start by introducing the parameterized Bellman operator, and I want to first have here a quick representation of the regular Bellman operator. You know that it's always an operator taking a Q function as input, then gamma is the Bellman operator, and you need the projection step back. This will give you the next Q function, Q k plus 1. Our parameterized Bellman operator, or PBO, does something slightly different. Now we don't operate on Q functions, but on the parameters of the Q function. So we learn a function that takes as input the parameters of the Q function. In this case, we call them omega k, and outputs the new parameters of an updated Q function that we call omega k plus 1. And now we can do something that we cannot do normally with a regular Bellman operator, which is possibly taking the output of this PBO and re-injecting it inside as an input. So we can effectively create a self-loop where the Bellman operator, our PBO, can update parameters consecutively without projection steps that are needed and are expensive and time-consuming and so on. Okay, so this is the formalization of what we do. Let's see a bit more in detail what are the advantages and the differences between the regular Bellman operator and our PBO. So, the regular Bellman operator always operates on one-step application of the operator, so this means we are slow. It is sample dependent, meaning that every time you apply it, you need a transition or more transition, state, action, reward, next state. And you always need a projection step to go back in the function space. So this makes the whole thing slow, data inefficient, and also computationally inefficient. In PBO, we can do an arbitrary number of steps. So we can, as I said before, re-inject the parameters as input as many times as we want. We are sample independent because this function, once it's learned, doesn't need samples anymore. It only needs the input, the parameters, and the output that can become the input in the following step. And there is no projection step back in the function space. So these are our theoretical advantages. Then there are, of course, some caveats that I will explain you quickly. First of all, how the PBO is learned. How do we obtain a PBO? Now, the goal is to simply try to learn to imitate the behavior of the optimal Bellman operator. So we want a function able to really understand how the Bellman operator operates in the optimal case and in expectation. In expectation because we want to make it detached from each individual sample. So what we do is to minimize this loss. This loss, it's not so much different from what we have seen before, the gamma star Q minus Q. But here we have the important point that we are not minimizing the loss by optimizing the parameters of the Q function, but we optimize the parameters of the PBO itself, so the parameters phi. And if you see, this loss contains two sums. So we have a sum from k equal 1 to k equal capital K. These are all the approximations of the updates that we try to do with our PBO. So for example, if k is 10, this means we are trying to minimize this loss for 10 consecutive updates of the PBO. The other sum is on the samples. So we have the data set with state, action, reward, next state, and also some data of parameters of Q functions. So we are basically learning how the Bellman operator works for different Q functions that we can also, for example, generate randomly by generating the parameters omega, and we minimize this loss. So here we can consider omega fixed, static parameters of the Q function. We are only changing the ones of the lambda, so the PBO that we are trying to learn. And what happens in the function space is this. So in the AVI setting, our setting that we have normally in function approximation with the QN and so on, we are, as I said, proceeding gradually, step by step. In our PBO, we can do something more. So if, for example, your budget of updates is K in the QN, SAC, DPG, and so on, you will stop after K updates. And you cannot do anything else than simply taking the Q that you found and use it for deployment on your agent. In PBO, we can do something more. So if you want to learn a PBO able to represent K updates of your Q function, you will definitely be able to reach the kth update, so reaching this point in the function space. But since you have this function now replicating the Bellman operator, nothing prevents you to simply use it to move forward. And hopefully, if the function is learned quite well, this will move you farther towards the target that you are trying to reach. Of course, it's hinging a lot on the fact that the PBO is accurately representing the Bellman operator. So you are hoping that you learned how to generalize the Bellman operator for multiple steps. So in this blue line on the right, you can see that we can proceed further, more than the budget that we have allows us to do in the AVI. PBO is just the tool, let's say. After developing the tool, we made some algorithms that are kind of exploiting the benefit of PBO. So we started using FQI and DQN. They are both value-based techniques for learning Q function. And they do effectively what I told you before. So they do the projection step from to bring the target back in the function space. In PBO, we can do something more. In PBO, we can do basically all the K updates at once, because we can go from the initial Q function 0 outside of the function space with the gamma star Q0 going back to Q1. But then we can use Q1 as a target for also the next step of update. So gamma star Q1 to go back to Q2. And this can be done for all the K steps that we want to do in the future. So we are learning a whole path of Bellman updates from the initial one till the K1. And this gives us the idea that we can generalize to multiple steps for multiple samples, hoping to find a nice Bellman operator replicating the real one. If we think about the bound we have seen before, we can see that while FQI is really trying to minimize the approximation error step by step, so it's only focusing on one step every time to minimize this approximation error, we are able to minimize all the K approximation errors at once, because we are minimizing the losses over multiple Bellman updates. So this gives us hope that we are effectively minimizing the upper bound and then also speeding up convergence to the real Q star. I can show you some results here. First, in a simple LQR problem. So in this histogram, we are showing the difference between the optimal parameters omega star that we can get in closed form in the LQR problem, and the results that we get with FQI and some ablations over FQI and our PBO, some different variants of the version of PBO of FQI that we use with the PBO operator. We can see that in general, we leave a budget of K2, K3, or K4 for the updates of FQI, and it's clear that FQI cannot go beyond that. So in the case the budget is K2, FQI can only do 2 updates. In the case it's 3, FQI can again do only 3 updates. But it's nice to see that we can do something more when we use our version of FQI using the PBO, so the projected FQI, we call it. We can do, of course, 2 steps of update, but we can proceed also doing 5, 8, or as many as we want. And the real advantage that we see here is that if we only learn PBO for 2 steps, and we apply it for 5 or 8, or in this case, we learn it for 3, and we apply it for 6 and 9 updates, the error in the learning of the weights is effectively decreasing the more we proceed. So we are able to show that even if we are learning PBO to be able to do only 2 steps, still it's able to generalize to multiple ones, and we can proceed minimizing the approximation error even more than just for 2 steps. This makes the whole thing sample efficient, faster, and in this case also more accurate. We can also see in the space of parameters here how FQI stops quite far from the optimal parameters that are marked with a star, while ProFQI, our technique, goes closer and closer to the real parameters. We also applied it in some simple, again, problems like car on hill, a different version of mountain car, bicycle and lunar lander. Here we are showing performance. Again, with the dashed black line, you can see the budget we allow PBO and FQI to learn. So in this case, it's 5, here it's 9, here it's 15. But we can still proceed after the budget that we have. So we can show that ProFQI can have also good performance if we make it work for more than the allowed budget on the K updates. Here we have the Q function we find, sorry, the policy we find after applying PBO, and it's this one, and here is the one that we find by applying simply FQI. If you are familiar with mountain car or car on hill, or Caron Hill, you will see that the shape that we get on the left is way more accurate to the real policy that we should get in this problem compared to the right one. And also we applied the PBO to DQN in the so-called pro-DQN algorithm, where we can still show that we are able to obtain either better performance or faster convergence also in this case. Okay, so let's now recap a bit the pros and cons of PBO, because we have seen some nice properties, but there are some, of course, disadvantages. So the pros are that we are able to do multiple Bellman updates at once. So we are sample also independent, which is also nice for sample efficiency, of course. And in some cases, this gives us faster convergence. However, the cons are that we need significant time to learn PBO itself. So PBO is not something easy to learn, as you can understand. It's been easy in these simple problems, but really, when you increase the complexity of the problem, it doesn't work so much anymore. What happens? Okay. It needs many samples to be learned too. So it's not something that it's completely sample inefficient. It's sample independent. It's sample independent once you have learned it. But to learn it, you take time and samples. And does not scale. So unfortunately, since we have in input and output the parameters of the Q function, if the Q function is big, so with many parameters, the whole thing does not scale anymore. So the idea is we still have get something nice, which is the possibility of going beyond one step of update. The question is, can we have the same benefit of this method while still being able to scale? And the next works are trying to do something like this. So let's recap the idea of the Q network. In Q functions approximation, we always have this idea where you have the online network and the target network. If you are familiar with the QN, you know that you need a semi-gradient update where you have a fixed target and the online network trying to learn the fixed target. We present an approach called iterated Q network, where we do something similar to PBO, but in this case with Q functions involved. So we are not anymore updating for a single update of the Bellman update, but we are trying to model multiple Bellman updates at once, this time operating on the Q function. So we have a loss that doesn't anymore simply minimize the difference between one target and the online network, but it's a loss over the sum of multiple errors over time. So it's the sum of the standard one plus the following k updates of the Bellman operators. To realize this, we adopt a simple, let's say conceptually simple, multi-headed network where we have, for example, a network with a shared convolutional layer for processing Atari frames, as is commonly done, and then multiple heads where each head will model a consecutive update of the Bellman, of the Q function. So for example, the head 1 will be the Q function after one step, head 2 will be the Q function after 2 steps, and so on. So if we have k heads, we will have k updates at once for each state in input of our model. We call this iterated DQN, IDQN. Let's see how IDQN works in the function space. So the Q network, now I think it's clear, really operates step by step. So we go outside of the function space and we come back and we do it multiple times. With our approach, iterated Q network, we can again minimize the losses over multiple steps at once. So since we have, for example, in this case, 3 heads, we are able to minimize 3 losses at the same time. So we are not only training the Q function for the next step, but we are preparing the future steps to be already kind of pre-trained, so pre-minimized, for future updates too. So it's a whole chain of updates we are doing to prepare the future ones to be already in a good position to be optimized. And one limitation of PBO was that if the budget was k, you were only able to learn k steps. There was no way to, let's say, move forward. While here, by having a fixed number of heads, so if we have, for example, k heads, we need a way to move forward. We cannot really do the Bellman update for only k steps. And the way we found was to do a window shift. So if we have 10 heads, we learn 10 Bellman updates. Then we freeze the initial one, and we use it for learning the 11th one. So we are, after some updates, we are stopping our learning procedure, and we are shifting one step. This allows us to basically move forward towards possibly infinite steps of the Bellman update. The thing is, the target networks here are playing a fundamental role for stability because this fly is really annoying me, because otherwise the whole thing will become really unstable. So the idea is that you need to really, I didn't really tell you all the details, but you need to really play nicely with all the target networks involved in this chain to guarantee some stability in the learning. Nothing really complicated, but you need to be a bit careful with it. So target networks are very important here. But the problem is that if you use target networks, you are kind of breaking the assumptions that we need for the ABI theory bound that we have seen before. So the idea is we are trying to minimize this bound, but not really, because target networks are creating problems to us. We offer a sufficient condition telling us that, let's say, in this situation, the bound is effectively reduced. So the bound is reduced, not always, but only when equation 4 is verified. Equation 4, it's a result we got from some a longer proof that I will omit here, but basically it's a bound over the displacement of the target based on the approximation error before optimization and after optimization. So the takeaway from this is that the bound we have seen before is actually minimized by our IDQN approach only in some situations because of the presence of the target network. In an experiment we have done just to see the benefit theoretically of our approach, again we take Caron Hill and we test the performance loss over different settings of K. So we use K1, which is just the DQN approach, and then K4, K7, and K10, and K20. We can see that this approach in Caron Hill doesn't really get worse if K increases. It actually becomes better and better as much as we learn consecutive K updates. In particular, the performance loss we get with a K20 parameter, it's actually quite good and shows a steady decrease in performance loss when, with K increasing. We also, finally, have been able to test this approach on more complex problems, because by being able to use Q functions and not anymore the parameters of the Q function, we don't have any problem to scale to Atari games, Mujoko, and so on. And in particular, we applied the iterated idea over different algorithms, so over DQN and IQN. They are all deep Q network techniques. We can see that over a set of different Atari games, on average, applying the iterated idea always improves the performance over the baseline. So you can see that iterated DQN outperforms DQN, and also iterated IQN outperforms IQN. Then there are some ablations on the number of gradient updates, on the number of target updates. We also ablated over some different settings where we use, for example, DQN with a 5-step return, or IDQN with a K5 plus 3-step return, and so on. So in general, applying the iterated idea always improves performance over the classic baseline. And really also scales to actor-critic approaches. So for example, we did some Mujoko experiments where we tested the iterated idea over SAC and DrawQ, again, showing performance boost over the baseline. The target are still a problem for us, as I said before. The sufficient condition is nice, but let's say we tried everything we could to get rid of these targets that were really annoying us. Like this fly is annoying me now. And we managed partially to do it, and then in the last work I will present you, we totally did it. So let's go gradually towards it. Let's recap quickly what target means in a value-based approximation. So we have the target approaches where in the normal case, so the classic DQN case, for example, we have a target that is frozen, and it's used for computing the target of the optimization for the online network that you can see here in green. This is the classic approach. In target free, which are almost never done because they are very unstable, you have no target that is frozen, and the online network itself is the target of itself. So basically you are kind of optimizing a moving target, and this makes everything very unstable, and usually it's never done. We proposed, just to test, let's say, an idea where we have a single network with some shared features. And just to clarify, green means moving, so something that is being learned, and gray means frozen. So in the shared features idea that we tried, we got rid of the target network in gray. We added a shared layer with moving parameters, and then two heads. One head is frozen, and this head is used for the target, and one head is updated to learn this target. So now we didn't really remove the target network, we just decoupled some frozen part with some moving part in a single multi-headed network. So this kind of worked, but it was nice to see that if we apply the idea of the iterated approach, in this case, we get actually very good performance. I will tell you why later, but I will show you first empirically how good the performance are in this case. So just what we have seen before. As you can see, we go from Q0 to Q1 to Q2 till Qk that we want to be able to learn. Here you can see in more detail what happens. I will probably not spend too much time here, but basically you can see the chain of updates. So above, it's our approach, where you can update multiple queues at the same time, while target-based, again, operates each step. We have some results on Atari on different architecture, for example, the convolution architecture plus layer norm, and the Impala architecture plus layer norm. We compare the target-based DQN, the target-free DQN, and then our approach with K1, 4, 9, and 49. We can see that the area under the curve, which is a way to measure performance, in our case, with K9, it's really outperforming all the other baselines. And also the IQM return, the interquantile mean, it's also showing some nice improvement. But the important thing here, because performance are not always giving us all the, all the interpretation of a method, is that we are using much fewer parameters than, for example, the target-based approach. Because target-based is using twice the parameters of the QN, we are using half of them. And even if you increase K to 49, it's just a minor improvement, increase of parameters, because the head, it's much smaller than the backbone that you have in the shared layers of the network. So for example, in the Impala architecture, there is not much improvement, there is no improvement actually, between target-based and our approach. But the difference is small, and the parameters are much fewer. So we can get at least some efficiency compared to the target-based. We also applied it in Mujoko in a Simba architecture, again showing some performance improvement and efficiency. And in a GPT-2 architecture in a Wordle task. So we simply applied it also in language-based problems. On the ILQL, the implicit language Q-learning. It's an algorithm from Berkeley to operate on language-based problems. And also here, we have been able to show performance improvements and efficiency. Now, I told you before, I would have showed you some reasons why this approach works. These are the reasons. So, at least empirically, we can show that the gradient of our approach is much more similar to the one of the target-based approach. So target-based is the most accurate, we can say. It's the slowest, but also the most accurate. And the cosine similarity between the gradient of our approach and the target-based is way higher than the one that we can have, for example, between target-free and target-based. So target-free, it's different and also more unstable compared to the target-based, because we can see that the target churn, which is how much the target is changing from step to step, it's very high for target-free, so it's basically 1. It changes completely from one step to the other, meaning it's really unstable and difficult to optimize. While for us, it's in between. So we are able to show that the target is not changing too much, but still it's changing faster than the target-based approach, for example. And the S-rank, which is a way to express how representative the features are, it's also higher for us. So in case we have ISDQN with K9, the features are way more representative than the ones that we have, for example, with target-based and target-free. So these are empirical reasons that are showing you why this approach can still outperform the other ones. What is missing here? We are back to our bound that for now we know very well. So again, we got rid of many target networks in this approach, but still we have the single target network in one of the heads of the network. So we are still not effectively reducing the bound as we would like to do. So we finally tried to answer this question: can we completely remove this dependency on target networks and effectively reduce the bound? Now, there is a nice category of works in temporal difference learning called gradient TD learning. These approaches are the one for which you are trying to remove the semi-gradient update, where you have a frozen target, and you are trying to minimize the Bellman residual, we call it. So you are trying to minimize the distance between target and Q function by operating on both. So we have here a moving target and a moving function trying to learn it. So while in TD learning, as you can see, each target is Q bar, meaning it's frozen. Here we have gamma Q0, gamma Q1, gamma Q2, and they are all being learned while also you are trying to learn Q2 itself. This, of course, it's a dream for us. It could be very nice if this was possible to be done, but we know that semi-gradient are needed to stabilize the whole thing, so it's not really easy to operate on gradient TD learning techniques. There are some works, but they are more involved than simply doing what we have done till now. So let's see a bit more accurate, at least what we want to do. We tried to apply our idea of the iterated TD learning approach on the gradient TD learning approach. Intuitively, nothing prevents us to combine the two ideas, and this is what we have done, to obtain the gradient iterated TD learning algorithm. So here we have the gradient TD learning, where we are changing both target and online network at the same time. The iterated idea, where we are optimizing over multiple Bellman updates, and the gradient iterated TD learning, which does both of the things. Now, as I said, it's not really so simple to do. So we took a working algorithm for the gradient TD learning techniques called TDRC. This is a method from Alberta that effectively learns the Q function even if the target is moving. This is done by having an additional function to learn called H, which I will also here not really go into the details of this. But this is the architecture they use. And our solution was to combine the architecture of TDRC with our ITD learning to obtain the combination of it. So our iterated gradient TD learning technique, where we have multiple Q functions and still also the use of the H function to stabilize the whole learning of the gradient TD learning steps. Okay, so we take, for example, the Baird counterexample. This is very famous as a way to show how TD learning can diverge in the case of policy learning. Normally, temporal difference techniques here, when you are using linear function approximation and of policy data, they are diverging. And you can see, for example, here the value error for TD, it's exploding. It's exploding also for the iterated temporal difference technique. So if you apply IDQN or IFQI and so on the Baird counterexample, this will also explode. It's nice to see that the combination of the gradient TD learning approach plus our iterated one is able to not make the whole thing explode and actually minimize the sum of Bellman errors. So we are able here to minimize the error as we would like to do. And the value error also is decreasing, and nicely it's also decreasing more than for the TDRC technique. So we also have been able to show some improvement over the previously developed method for gradient temporal difference learning. Again, by acting on Q functions, we are able to apply the whole thing on Atari and Mujoko problems. Here we tested over 10 different Atari games, 6 Mujoko tasks, and also in an offline setting, again on 10 Atari games. We can see performance improvement over the baseline, which is DQN here. Here it's SAC, and here it's CQL. So this gives us the idea that we have been able finally to show performance boost, plus adhering completely to the bound and actually also minimizing the upper bound for the convergence speed of our algorithm. And this leads me to the end of the talk. So the key takeaways we can get from our works are that we tried progressively to minimize the bound of the AVI I showed you before, but still trying to be able to scale to more meaningful problems than Caron Hill, Lunar Lander, and so on. With PBO, we have been able to completely reduce the bound, so to adhere to the theory as we wanted, but we have not been able at all to scale to deep networks. But we didn't have any target network, so at least for this, it was efficient. For the iterated approach, we partially addressed the AVI bound for the sufficient condition I presented you before. We have been able to scale to deep networks, but in the case of IQN, not been able to remove the target network dependency, while for the shared one, partially because we have less target networks at least. In the final work that will be presented in RLC in summer, we have been able to nicely obtain every goal we had in mind. Okay, and with this I want to thank my co-authors. Theo was the first author of all these papers, so he will be also in RLC and happy to talk to you if you are there. I also want to thank Marta, Adam, and Jan, and all the other co-authors involved in all the papers. And thank you for listening, and I will be happy to answer your questions.
Thank you for your interesting talk. Very nice idea. Maybe I didn't get it right, but if you apply 7 Bellman equations, Bellman operators after each other, that's not the same thing as taking 7 time steps, right?
Yes.
Have you thought about combining the two?
So you are referring to PBO, I guess, right? To the parameterized Bellman operator.
Yes.
Example. So let me see, I can go back to the function space example I showed you. For example here. So the question is, applying 7 Bellman updates is not like applying 7 steps. What do you mean by step?
Time steps. So
time steps.
If I mean the Bellman operation, you only apply once, right?
Yes.
But it's not the same as 7 actions being taken.
Yeah,
like
actually
it's n step DQN or so.
Yes. So actually in this work on PBO, we operate on an offline setting. So we take offline data and we try to learn how the Bellman operator works for data that we collected before. And we also generate randomly the parameters of the Q function, because the Bellman operator works on any Q function that you have, and we apply 1 step. So for 1 step, I mean 1 update that you can see, that you can use to see how the Bellman operator works. So if you say that you do 7 steps, we are basically doing the iteration over the PBO for 7 times. The time steps here are not really involved because there is no deployment of the PBO in the environment before you learn it. So the whole thing is using the offline setting to learn the PBO, and once it's learned, you simply deploy it to approximate your Q function. And once your Q function is found, you use it on your agent. So there is no time step concept, let's say, in PBO till you learn it and you start applying it. And in IDQN and so on, it's the same. So in IDQN, it's basically just a way to anticipate what the Q function will be in K steps in the future. And then once you have the Q function after K steps in the future, you can use it for your time steps in the environment. So it's a way to, I mean, I see them as a decoupled thing. Time steps are the way, the times you use the Q function to compute your policy and to do actions in the environment. But the Q function itself, it's simply telling you the future in some sense. It's telling you the Q function is going to look like this after K steps.
Okay, thanks.
Thank you. I hope I answered your question.
Right, we are going to have to move on in the interest of time, so thank you again.
Thank you.
Very nice visuals in your talk. I really enjoyed that. So the next on the schedule is the coffee break. So some of you have already discovered the coffee room. That's going to be that way. So you follow the stairs, go up, and then you'll see a big room with glass and coffee inside. That's also where the poster session is going to take place. So you'll also see posters, and you can ask the authors about their papers. You can also take the coffee break to ask our speakers any extra questions and discuss with them. One note is that the posters are going to be the same in the coffee session in the morning and afternoon, so don't feel like you need to be in a rush and ask all your questions right away. And then finally, it's important that we make it here at 11:30 sharp so that we can continue the program with the next speakers. So you have a little under an hour, like 50 minutes for the coffee break. So see you back here at 11:50.
Hello, hello, hello.
Test, test.
Okay.
Test. Test. Yeah.
Amazing.
Hi everybody, welcome back. So I hope you enjoyed the coffee break and the poster session with the nice snacks. So our next speaker will be Guillermo Alberto Perez. He's an associate professor at the University of Antwerp. Before that, he was a research assistant and got his PhD from Université Libre de Bruxelles and spent some time as a visiting researcher at the University of Oxford. His research interests include logic and computer science, automatic theory, formal verification, and trustworthy AI, and we're looking forward very much to your talk today.
Test. Can you hear me in the back? All right. Thanks for the introduction. Maybe I'll spend some time on the title to unpack some of the words. Let's start by BeNeRL. I got the invitation from the organizers, thank you very much, and I thought it was a very nice venue for me because, you see, I work in Belgium, in Antwerp, but I live in the Netherlands, so I commute to Belgium to work. And then my colleagues, I still think I'm a young student working on automata and logic, of course, but my colleagues from then, they keep telling me that nowadays I'm actually only publishing at AI venues. And so I haven't had the courage to go and check the numbers, but I guess it's probably right. And so BeNeRL is actually a very nice venue for me to give this talk. And the topic is going to be some work that I did 2 years ago with colleagues from France on classes of partially observable MDPs that are actually decidable. And a bit more recent work, which I think is a bit more exciting, but I'll let you be the judge of that. Good, and so the main question that I want to address is how do we balance the main problem with POMDPs, and that is that they are extremely expressive. They allow us to explicitly model stuff like sensor noise, hidden modes, and partial feedback, but they are also a bit too expressive, because anything that you want to answer about them algorithmically is going to be undecidable. And so I'm going to come back to this in a second with some examples of what is actually undecidable. But before that, maybe by show of hands, who has ever worked with POMDPs or modeled something with POMDPs before? Okay, that's most of you. And maybe to get 100%, who has worked with MDPs before? Okay, good. So if you did not raise your hand the first time, I'm just going to throw at you the definition of partial observability in a few slides and give you an example. So you should be able to make the step from MDP to POMDPs pretty quickly. But let's get back at the question here. So there's two ways in which you can approach it, and I really want to make the distinction here because the way in which we usually do it with RL is we get data, or we try to interact with the environment to try and get a good policy or approximate a good policy with some guarantees, all right? Finite time guarantees, or that means a finite horizon, or you want to keep improving your policy, and in the limit, you get some optimal policy, all right? But the way in which I want you to set your mind for the next 25 minutes or so is to think about what would happen if you put RL in your pacemaker, right? You want hard guarantees, right? You want to actually offline compute a policy so that you get a policy that satisfies some hard constraints. And this is a bit closer to what people in formal verification and formal methods do, which explains my background, of course. But it's also something that you want in RL if you want it to be deployed a bit more widely, right? And so this is what we want to look at, and this is why the undecidability question is a bit annoying. And a bit of a spoiler, so this talk in one line, essentially I want to tell you that there's a way of recovering decidability if you make sure that the partial observability is not completely rampant in your problem, all right? Okay. And so if you've ever attended a POMDP talk, you know that there's two things that will always feature: a very small toy example and the belief update function. So let's start with the small example. Here I'm going to focus on Tiger. And this is an old but useful, I'd say, for this talk example, because it helps me introduce the concept for the restrictions. So you wake up one day and you're in the room. This room has two doors, and you hear by a speaker that there's a tiger behind one of these two rooms, all right? And so the only thing you can do is wait and listen to maybe figure out on which side the tiger is actually at. Or you could open the door. In the other door where the tiger's not at, there's an exit. Okay? And so the room has really bad acoustics, and you could get some echo, and you hear for a bit, so you wait to listen, and you actually hear the tiger here, but it's on the other side, and then you make the wrong decision. So there's a small probability that you hear the tiger where it's not really at. And I hope it's clear that you don't want to starve to death and that you want to make it out of the room. Okay, so that's the objective. Any questions about the example? I guess you've seen it before in some POMDP talks, some of you. Good. So that's the intuition, and this is the horrible model, or maybe it's not so horrible if you've worked with MVPs before. So you see, we have a few actions. We can wait and listen. We can open the right door. We can open the left door. And if you're in the left state, after you listen, you have a distribution over the possible states. So in this case, you stay on the left because the tiger stays on the left. And you also get this distribution over the observation signals, right? This is the noisy observation of, well, if you're on the left, if the tiger is on the left, then you hear it on the left, but with some small probability, you also hear it on the right, okay? And then you could also open the doors, and depending on where the tiger is actually at, you can die or survive. And this happens with probability 1 after you open the door, all right? Any questions with the model? On the right? Okay, yeah. Say again? There's no cost, but of course, like I said, you don't want to starve to death, so you want to eventually open a door. All right? Good, so this is the model, and in POMDPs, or in dealing with POMDPs, we've figured out that there's something that's pretty useful, and that's dealing with the belief. All right, so that's the second component I told you that's going to feature here. And the belief essentially tells you how likely you think, what the likelihood is of being in a particular state. And so let's assume we start with a uniform distribution here. You don't actually know where you're at. And when you wait and listen, if you hear the tiger on the left, you update your belief using some Bayes-like update. And you end up thinking that you're on the left with 0.8 and on the right with 0.2. All right? So this is your update of your belief. And you can actually build this tree. It becomes, in general, an infinite tree. But what's nice about it is that the sequence of actions that you played and the observations that you've gotten tell you what the likelihood is of being at particular states. Right? So you can base your decisions on that. But that's also a very bad thing about the belief. So you can think about it both mathematically or also implementation terms. Mathematically, the tree could be infinite because you can start getting very small probabilities or unbounded precision that starts to converge towards some number. And if you want to implement this with floating point numbers, then you start making very big mistakes. So you don't want to do this. And from my perspective and my colleagues who are also working with automata theory, you know, we like sets. We don't like numbers. We like sets of states. We like subset constructions and pumping lemmas, right? And so this is what we tried to do for this work. We were wondering, what can you do if you forget about the numbers? What if we only look at what's possible? Not what's likely, but just what's possible. What can you still solve with this kind of abstraction? Because if you focus only on the belief supports, you still have a lot of them, but it's a finite set. So all of a sudden, things that were undecidable becomes decidable, even if they're a bit hard. Okay, so let's take a step back and try and motivate why really you need all of this horrible machinery to solve these problems. Why is it really that POMDPs are hard? And I'm going to try to explain to you which problems are hard and why they are hard. Essentially, anything you ask about POMDPs that's a serious question is going to be undecidable, all right? If you want to give me a POMDP and you have a happy face, somewhere a state that's a happy face, and you want to ask, is there a policy that reaches this happy face with at least probability 1/2? Undecidable. If you want to approximate the optimal value with which some policy can reach this happy face, undecidable, all right? If you want to go crazier and you combine a few objectives like I actually want to avoid some bad states, I want to reach some good states, and eventually I also want to start avoiding some other states, we call this sometimes omega regular or parity objectives. Then this is undecidable even if you ask, can I do this with probability 1? Is there a policy such that with probability 1 you satisfy this crazy combination of objectives? It's just extremely hard. You don't even have to care about the numbers. This qualitative question of can I do it with probability 1 is also undecidable. So almost anything that you ask about POMDPs really is undecidable. Notice that I haven't even added rewards here. That makes everything harder. And there are multiple sources for this thing, but I want to highlight one of my favorite papers that shows bad news for POMDPs. This is a work by Madani, Hanks, and Condon, where they have a diagram. Well, this is the diagram. I took a screenshot. They essentially start from some finite automata question, which is known to be super hard. And then they list all of the problems that they can think of for POMDPs. And they start relating each one of them so that in the end, everything in the diagram turns out to be undecidable by reduction from this finite state automata problem. And so my advice, if you're working with POMDPs, the first thing you should do is go and look at this paper, see if you can match with one of these problems, and then it's just your problem is undecidable. So you can go crazy with heuristics and you can motivate everything that you're doing. But I want to argue that the reason that these things are hard is really because of this unbounded precision that you need in the belief tree. So as long as you can get rid of this, or if your belief tree turns out to be finite, then you should still be able to do something about it. And this is a bit what we're going to try to do here. Good, and so now I've gotten to the first restriction, or the first class of POMDPs that I want to introduce, and it's extremely simple. Like I said, I'm a humble automata theorist. I just want subsets. So let's introduce the concept of a revelation. So in a POMDP, you have a revelation if your belief collapses to a single state, right? You know for sure that you're at this state. You may think this is a very weird thing. It shouldn't happen that often. And so we introduce now two classes of POMDPs. The first one just says, no matter how you play, infinitely often you should get with probability 1 revelations. And this looks like a very strong constraint, but actually in RL we are already assuming this, because in almost every paper we start by saying our MDPs are ergodic, or POMDPs are ergodic. So that means that infinitely often you reset, for instance. This is one way of enforcing this. And so it turns out that most of the POMDPs we work with are weakly revealing. Strongly revealing is a bit stronger, as the name says. It's not that infinitely often you have a revelation, but actually every step you take has a small probability of revealing to you the actual state at every time step. So you don't have to wait a bit for it. At every time step, there's this small chance that you actually get to see the state. So the intuition behind this is that maybe your POMDP or your policy can forget about what the environment looks like, but every now and then you actually refresh your knowledge and you have full observation of what's actually happening. And it's good to look at an example to try and differentiate the two classes. So here's a POMDP in which I replace the observation signals by colors. So if you land at Q1, you get the observation signal red, and the same thing with Q1 prime. So these two guys they get the same observation signal and they're indistinguishable in a sense. So this guy is not strongly revealing, and the reason is because if from Q1 you play an A, you can land at Q1 prime, and there you get an observation signal of red, but this can also happen from Q1, all right? So it's not really a revelation, you still have some uncertainty. But it is weakly revealing because of what I told you earlier, this guy is ergodic. No matter how you play with probability 1, you're going to hit the blue state again and again. And so that means that you keep refreshing your, you keep getting revelations every now and then. Questions about this? Okay. Good. So maybe some bad news, and what was the motivation for the later work that I will introduce in a few slides, is that Tiger, even though it is a very simple POMDP, it is not revealing. It is not strongly revealing. But we can actually modify it because we're humans and we're multimodal, right? So we don't have to listen only for the Tiger. You can put your hand on the door, and then if you put your hand, you actually know if the Tiger brushes against the door, you feel it, and then that's a revelation of sorts, right? So I have modified here the POMDP so that you see that you have a left with an exclamation mark if you play listen from the left. And that just means you actually felt the Tiger there, right? So this is, it has nothing to do with the echo. You actually know that the Tiger is there. It's a revelation. And now I force the Tiger POMDP to be strongly revealing. Good, so what does this buy me? It's a restriction, so that means that now I have some POMDPs that are revealing and some POMDPs that aren't. And so the question is, what can I solve now, all right? And there's a spoiler there, but here are the actual theorems. If you have weak revelations, then combinations of this, some combinations of these crazy objectives that I told you, like avoiding bad states and reaching good states, now I can actually compute a policy to try and do this with probability 1. Or I can tell you for sure that that 1 doesn't exist. And if you have strong revelations, then any combination of these crazy objectives that I told you about, you can also find a policy for this or prove that 1 does not exist. All right? So we went from an undecidable situation to a very nice case. It's still hard because we're dealing with subsets, but it is now possible. In the paper, we have this very nice hierarchy of what you can actually recover in terms of decidability and what is still hard. And there is some follow-up work. If you ask me about it later, I can tell you some people have refined of what you can actually do with strong revelations. So it turns out that it's a very nice restriction, and you can do way more than what I'm presenting here. But what I think is the nicest part of this work is the policies that you get, right? So when you do find a policy that satisfies your properties with probability 1, you find one that looks like this. So the policy just acts on subsets. And so if you're thinking of some gym environment and you want to put an observation wrapper on it, you don't actually have to keep track of the probabilities. It suffices to keep a list of the current possible states. And then you can actually, you know that if there exists a policy that satisfies some objective with probability 1, then something like this, it's what you should be finding. Any questions about revelations? If not, I'll move to the other restriction that I want to introduce. And this one is a bit more convoluted. So bear with me. This is called posterior determinism, all right? And so the condition asks, if you take a state and you play an action from it, then this plus the observation signal that you get should uniquely determine the successor, all right? There shouldn't be two successors with the combination of source, action, and observation signal. So here it is in a picture. You start from Q, and then if you play the action A and you get the observation signal O1, so the blue, it should only be possible to go to Q1, not to any other states. And similarly, with O2, you should only be able to get to Q2. I am not saying that you will know that you're in Q. I'm just saying that this is a structural restriction that I'm going to put in the POMDP. And what this restriction is going to buy me is that if at any point the state actually becomes known, you never lose that information. So you will be able to keep track of where you're at. I know that it is a convoluted definition, so let me try and motivate it by telling you which other POMDPs are in this class. So MDPs, the classical MDPs, they all fit into this class. Tiger is actually posterior deterministic, because you're on the right or on the left, and then you stay on the left or on the right. And this studied class of deterministic and quasi-deterministic POMDPs that I will not introduce is also posterior deterministic. So we're not making a new crazy class of POMDPs. This actually encompasses known work. And again, the invariant here is that belief supports can shrink, but they will never grow, because of this property of posterior determinism. So we have a sort of monotonicity in how we're losing the information. And I think personally that a nicer way of looking at posterior determinism is to focus on this subclass of POMDPs that are called multi-environment MDPs. And so a way of introducing this is we have multiple copies of the same MDP, but you have different dynamics. So here I have two MDPs, and on the left-hand side you have this blue dynamics that rotate your state clockwise, and the red dynamics rotate you counterclockwise, but you don't actually know on which one you start. So you have some initial uncertainty that you can resolve while you're playing, and this is also posterior deterministic, all right? And this is also being studied right now in formal methods and AI as restrictions of POMDPs. I should be a bit careful because it is a POMDP only if you assume at the beginning that you have an initial belief, and this is called the prior semantics. You could have a stronger semantics on which you actually want to satisfy some constraint for all possible states in the initial belief support, but there's a way of connecting these two semantics. But for the most part, for POMDPs, we're in the prior semantics world. Okay, new restriction, and so what are the new things that I can do? This posterior deterministic class of POMDPs is so nice that now you can even approximate the value of satisfaction of something. So you can get the maximal value with which you can guarantee to satisfy some condition, all right? With, so in this case, I'm claiming it for reachability. With multi-environment MDPs, you can go further and actually do it with parity objectives. So those are the crazy combinations that I told you about concerning safety, reachability, and eventual safety. And so what's even nicer is that this multi-environment MDP thing is not really a restriction in terms of expressiveness. You can actually translate any posterior deterministic POMDP into a multi-environment MDP. So that means that you can do everything in the multi-environment world as long as you're willing to pay an exponential blow-up. But honestly, I think it's more intuitive to think about multi-environment MDPs. They're just a copy. Okay, and this is my last technical slide. I will not say too much about this, but the price that we're paying with posterior deterministic POMDPs is that I give up on just working on subsets. And I have to go back to dealing with this belief tree. But to make algorithms, I need to make sure that it is finite, right? And so here's an example in which you could be at Q1 or Q2, and you keep playing this action A. Eventually, we know you will hit Q3, and you will know for certain, because of the property of posterior determinism, that you previously were at Q1 and before that at Q2. That's this green branch, and we can actually prune the tree at that point. And so the only thing smart that we're doing in the paper about posterior deterministic POMDPs is to find conditions where you can prune even when you don't have a singleton, all right? Because the probability is just getting very, very small. So that's the only smart thing that we're doing in the paper. All right, I'm done with the technical stuff. I'm just going to try and summarize everything I said. I have a few classes of POMDPs on which I can give you exact algorithms. So no approximations, really exact algorithms to find a policy. And there's two classes that are related, posterior deterministic POMDPs and multi-environment MDPs. But the connection between posterior deterministic and revealing POMDPs is actually non-existent. They're orthogonal constraints that you can put on POMDPs. They both buy you different things. So if you're interested in satisfying something with probability 1, I think it's much nicer to work with revealing POMDPs. You only have to work with subsets of states. But if you actually want to approximate values, then you need to work with posterior deterministic POMDPs. Or even nicer with the multi-environment MDP thing. So it's different models, different restrictions, but I would say that the theme that has been driving us is how can we restrict the loss of information so that we can get something that's still decidable. And so you may have noticed that I am more on the theoretical side of RL, but if I were forced at gunpoint to use this stuff for practical applications, I would use this decision tree. So if you have full observation, use it. There's books on how to solve MDPs, and there's tools on how to do reinforcement learning, right? If you have revelations, if your thing is ergodic, and you know that you will get eventually some precise knowledge of the state, then use revelations. If you have a hidden persistent parameter that's set only at the beginning and you are not losing information about it later, then use multi-environment MDPs. And then otherwise, I hope you have posterior determinism, because that's the last thing that I know how to solve. If you don't have any of these properties, then you send an email to me and we start a new collaboration on a new class of POMDPs, all right? That's the last step. Yeah, so I should highlight, this is really for exact tools, right? I'm not saying that this takes over from RL. This definitely does not scale if you want to put it in practice. So there should be a nice combination of, a nice interplay of trying to learn stuff and actually get guarantees for the parts that matter, the parts that are safety critical. And so as a takeaway, I told you, or I reminded you that POMDPs are really hard. They don't have to be hard all the time. You can just try and control the information loss. And I told you about two ways of how you can do this, either by counting how many times and how often you get revelations, or by looking structurally at how you lose the information via the partial observability. And so, yeah, they remain hard, but in principle, you can still solve something for POMDPs, right? Good. I think I'll leave it there. Thanks.
Okay, thank you, Guillermo, for the very interesting talk. We have time for a couple of questions. So, anyone has a question? Yeah. Okay, one and then behind.
Thank you for the nice talk. I had a question about revelations. I can imagine that if your environment is very complex, that having a revelation from time to time still doesn't give you the opportunity to prune back, to really know where you have been and use that information. So is it then not true, like revelations are nice, but it also depends on the environment, or is it the other way? Or is it always true that if you have a revelation, you're always on the good side?
Okay. Yeah. So to repeat the question, we want to know whether revelations are nice in general, or if other structural restrictions combine well with revelations. It's rather the latter. So I'm cheating a bit, and I'm telling you we have very nice policies that depend only on the subsets. But the way in which they achieve what they do is by waiting in some cycles until the revelation occurs. And so that means that if you have really bad structure and you have to wait for one revelation and go try to do something else to get another revelation, then you will get stuck for a very long time. So in expectation, we know that will be exponential time before you can actually make progress. So yes, you need stronger structural restrictions so that you see that your policy makes progress fast.
Hi, thanks for your talk. I had a question about the posterior deterministic POMDPs. Is it a local property or a global property of the problem?
Yeah, good question. The way I introduced it is it is actually a local property. So you have to look at every transition from every state and see if this is satisfied. It translates into a global way of, or into a global guarantee that you're not losing information. So it has a monotonicity condition. So if you're thinking about how do we detect it, it's very easy syntactically to detect it.
Thank you.
Okay, one last question. Okay, then thank you very much, Guillermo. Okay, now it is my pleasure to introduce Kevin Luck. Kevin is an assistant professor at the Computational Intelligence Group at the Free University in Amsterdam. His research interests include combining deep reinforcement learning with evolutionary principle, AI-assisted design methodologies, and embodied intelligence. And judging from the title of the talk, I'm pretty sure that is going to be the content, but no spoilers. Okay, thank you, Kevin.
Yeah, thank you so much for the introduction, and also thank you for inviting me. So indeed, actually today the talk will be a bit more applied. So basically a subtitle could be cool things to do with reinforcement learning in robotics. So we are going to stay a little bit more high level. And unfortunately, I do not have enough time to actually go into all the details because I was a bit too excited. And I do know that I will be very hard at the time limit, so I may need to skip a couple of slides to actually get to the end of the talk. I just mentioned this because people are always a little bit surprised that we do robotics at the Freie Universität. We are not really good at advertising that, unfortunately, but in our lab, actually, so in the team I'm working on, actually, we do a lot of reinforcement learning, deep learning on real-world systems like humanoids, robot arms, and also quadrupeds. And there's also like colleagues who actually work on drone research. As I said, unfortunately, we are not so good at advertising this at the moment, but we do robotics. Okay. In today's talk, actually, I will first go into the first theme, which is basically how we can exploit morphological intelligence or find morphological intelligence with reinforcement learning, actually. And the second theme is really a bit more about going into the direction of large VLAs and large foundation models, actually how to increase the inference and the reaction times, as well as the energy efficiency with an approach we are presenting in ICHCAI in a couple of weeks for text-to-policy learning, actually. Cool. Let's dive in. Okay, so if you do robotics, we have basically like this cool thing, or like not really a cool thing, like a problem basically that if you build up a lab or you set up a lab, basically the first thing you're going to do is like you go online and try to shop for a robot arm, right? On the other end, there are the mechanical engineers or the robotics companies. They build these robot arms, but there's not really much communication between the two. Usually, if we have PhD students who do robotics, they leave at some point for industry, join these companies, but from that point on, there's like not that much interaction between the AI researchers, who do also reinforcement learning, of course, and the mechanical engineers. Like I said, so there's basically like a little bit this wall between these two worlds. But why not combine both, right? Can we not apply AI, machine learning, and reinforcement learning to design actually robot arms and control systems together? So this brings us to this idea of actually co-design. It has a lot of different names. So in the literature, it's co-adaptation, which I started using, and then co-design, which other people started using. I think there's also co-optimization. And then, of course, like if you use evolutionary algorithm, there's the whole field of evolutionary robotics. Little pun here with the revolutionary robotics if you use reinforcement learning. But the principal idea between all these approaches actually is pretty much the same, especially if you use reinforcement learning. Oops, trying to get that. So basically, on the left side, we have our behavioral optimization loop. So we usually define a reward. We follow basically our standard reinforcement learning recipe and try to find a good behavior for our robotic prototype or the current embodiment of our robot. Then if we are interested in also optimizing design, we have the second iterative design loop where we are actually given the good behaviors we found. We try to estimate with some machine learning method basically which design iterations of our robot we should try next. And of course, in the real world, we also have to manufacture them. And if we are talking about design here, it's really about, for example, like the length, the shape, the material of the limbs of the robot, right? Okay, so now if you look actually from our reinforcement learning view on this, right, we can actually treat this as an extension of a classic MDP process, namely like a contextual Markov decision process, right? So in this case, the context basically is just the design parameters, which are Xi here. So in Xi, of course, influences mainly the dynamics, right? So basically the dynamics function or like the transition function is influenced by the design, as well, of course, as the initial state distribution. And our agent morphologies can be discrete, but in our case, often we work with continuous design parameters such as length, for example, or shape. Okay, we still do actually optimize our cumulative return. The main difference here is just that we have now our expectation dependent on these contexts. And of course, we have also like a little bit degree of freedom in the policy we are optimizing. There are two main flavors which people have been doing. In robotics, that's very famous if you do domain randomization. So you change the embodiment. Basically, you'd often learn a policy which is embodiment agnostic, so the lower one. This policy is basically agnostic to the embodiment, is trying just to be really robust. Foundation models often use also this recipe. And then there are, of course, the embodiment-aware policies, which basically assume knowledge of the design parameters. So basically here the goal is really how can we exploit the embodiment and the morphology of the robot to the maximum, even if we change the limb length or the number of degrees of freedom of the robot. Okay, if we dive now a little bit deeper into the mathematics, actually it's an inherent bi-level optimization problem. In the inner loop, we basically do the classic reinforcement learning, right? So we try to optimize our policy, trying to increase our cumulative return. But now we also have the outer loop optimization, where we actually try to optimize our design parameters, which is a little bit of a chicken and egg situation. If we actually now look closer at this hierarchy is actually pretty much fixed, right? So at the bottom, we are trying to optimize behavior. At the top, we are trying to optimize the design parameters. The computational cost at the bottom is actually pretty high, right? So if you do robotics, we are basically amortizing the policy, right? So we could also throw an optimizer on it, but we need a policy because we want to do real-time control and high-frequency control, right? So like the more compute we actually have to spend during the action finding process, the worse it is. On the other hand, actually, the computational cost on the higher level, so on the design optimization level, is actually pretty low. Why? Because if you do practical robotics, you, of course, have to produce the robot, right? And this manufacturing of robots, so you can see actually on the left side in these videos the same type of robot, so it's like a paper robot. In the top part, you actually see the manufacturing process, and at the bottom, the learning process. The manufacturing process of a robot can often take days, right? So like also 3D printing actually takes several hours. So, and then of course we also have material costs, right? So, which also may change to some changes in the fitness function. So you also may want to account actually for the cost of the material or the personnel cost you actually spent on generating that. Okay, so coming back now to our co-design loop, which we have, right? So we have like the first approach which we are trying, or which we try to implement in 2020 actually is as one of the first, was actually we wanted to apply reinforcement learning on both sides of the loop, right? So normally, basically the design optimization happens completely independent, but we wanted to figure out how can we connect the reinforcement learning on the behavior side in an intelligent way to the design optimization side, right? And we came up with this, so the title is a bit wrong here, but with the co-design method, which is on the right side here actually, which basically works on the assumption that we always have only access to one robotic prototype. So on the evolutionary part, which is basically on the left side, so the traditional approach, you usually assume the existence of a population. We didn't want to do that because if you want to apply co-design in the real world, we do not have 20 robots, right? And if you want to buy 20 robots, that's maybe easy, but then you also need 20 PhD students for each robot. So like that's not really feasible. And the idea was really then through a really smart designing process that we basically figured out, so there are some tricks, but the principal idea was basically that we use also the Q function as a surrogate function for design optimization. That up to that point was not really done. Now since then, actually like many people are doing this now. So this has been like a really fruitful concept. So basically we try to estimate the future return by basically optimizing a design parameter with another optimization algorithm, right? So we're basically reusing the Q function, which we have to learn anyways, but we make sure that we use a contextualized Q function. Okay. And this works really well. So here we can show actually that we can optimize or find improved robot designs within 50 design iterations. This was, of course, done in simulation because at the time I didn't have so many people. So I was the PhD student actually. If you look actually though at the real world, at the simulation trials required, then actually you can see that this approach actually really brings down the computational effort because classical evolutionary methods actually they have to simulate. We did not have to simulate anymore thanks to the surrogate function. And another nice benefit actually is that you can actually traverse this landscape of optimal designs, right? So on the left side, you see actually one of the walkers which were optimized. There is also this cool design 24 where the walker figured out that if I shorten my leg, actually I can do these cool forward saltos, which was not optimal. So it unlearned it at some point, but it was a cool intermediate result. But you can also use the Q function and actually to analyze the design space and infer design principles for the design of your robots. Cool. Okay, so this was how we can do co-design with reinforcement learning a little bit smarter. Then in follow-up work, basically we are wondering, okay, so we have automated the upper two loops, right? So the behavior learning and the design optimization. But what about the reward function, right? So we all know reward functions to define is really hard. There are actually some works by, I think Peter Stone had a paper a couple of years ago where they did even human studies. Like humans are often not really good at reward function definitions, and it takes us some time to find a good reward function to find a good behavior. So our idea was here basically, can we not learn this, right? So can we not learn demonstration data, infer from that a learned reward function using a machine learning approach, and then apply our co-design process. And we actually apply this with adversarial imitation learning or inverse reinforcement learning, so basically extract the reward function. So basically this ties very nicely down into the inverse reinforcement learning framework, just that we apply it here also to the problem of co-design. We had two research questions. The first one was actually, does it help at all, right? So if we do co-design on an imitation learning problem, does it help us at all to improve the performance, right? This is not immediately clear. So if you give the robot basically the ability to change its embodiment, does the performance really improve? The second question was more a challenge because up to that point, again, many papers would usually learn a reward function, but then add in also a hand-engineered reward function, right? So some stability terms, especially with humanoids, such that actually the humanoid would walk upright. But we didn't want to do any of that. We really only wanted to use a learned reward function. Cool. First problem which we had to figure out was actually how to match human demonstrations. That's was a challenge because we didn't want to imitate the morphology of the human, right? We want to imitate the behavior. So we had to make the design or the state space which we use for the reward function design agnostic, right? So we basically use these markers on the embodiment of the human and on the embodiment of the humanoid, and we basically normalized it given the shape and the size of the robot, right? So we are working here in a normalized state space, and this was only used for the reward function, not for the policy. So the policy was actually working on the true proprioceptive data from the humanoid, but it was important. Cool. What we do then is actually we treat this as a state distribution matching problem, right? So the demonstrator implies basically this state visitation distribution where if of course depends on the policy of the demonstrator, which given is basically by an data set. On the right side now we depend actually on both the policy and the design variable, right? So we basically have a state distribution which depends here on the policy and on the design parameter. Both of these we can change, and this allows us to basically change the imitator both in the behavior and the design in order to match these two distributions together. And then what we apply in the co-design setting is basically an iterative process. So we first optimize the optimization by minimizing a divergence measure. So basically just a distance measure between two distributions, but ignored it as that distance. And then alternating every couple of episodes, we basically also try to optimize then the morphology, right? So we are then trying to match these two distributions, optimizing only the morphology parameter. Cool. What we used, we didn't use KL, we evaluated KL divergences, but it looks really good on the slides. So with Wasserstein distance is always a bit more complex. But we use actually Wasserstein distances, but KL divergence, of course, like one example, and it really nicely ends up with this, basically this expectation. And I'm going to skip a little bit the math and the algorithms at this point, but we basically just follow the standard inverse reinforcement learning recipe. So we train a reward function using this divergence basically, and then just apply standard reinforcement learning on that learned reward function. The results are pretty cool. So on the left side, you see the demonstrations, right? So they are just from the CMU data set. On the right side, you actually see the co-designed humanoids in Mojoko. And the really cool thing is actually, like, if you look at the top one, so the unoptimized humanoid is basically the blue one, and the design optimized humanoid is the orange one. That the orange humanoid has much more stable, much more natural gait, while the humanoid, the standard humanoid from Mojoko actually develops this crouching motion because it's like it cannot really match its dynamics to the demonstrations of the human. So we can basically say, yes, imitation learning is improved if we do also optimize the embodiment of the robot. The second one, the ball kicking one, so we didn't have a video of that, but basically the human is kicking a ball, I suppose. It's not tracked in the data set. Also here actually we can see that the co-designed robot actually is able to kick the ball, even though it looks really funny with a really small torso and really long legs, right? But the standard humanoid, which looks maybe more reasonable, basically only stumbles forward and is not able to kick the ball in the end. Okie dokie. I may just make it in time, so we may have enough time for the intermezzo. So we had it already like this morning in the first talk. There is actually an inherent problem, right? So like through the reinforcement learning process and also like the design process, we basically move from one design to another, right? So we have basically the sequence of designs. This is a problem because in reinforcement learning, this basically induces like an inherent distributional shift, right? The dynamics function changes, and therefore our policy always has to readapt to it. Excuse me. Okay, there are two different, like actually distribution shifts can affect, of course, like many different things. I think we had it this morning. So state spaces, action spaces, but also the transition dynamics, especially in the co-design problem. And you can see here one example from the work I'm going to show in a little bit, that basically these distribution shifts can really seriously affect the performance of the algorithm. So orange here is actually like a standard reinforcement learning algorithm. So it could not even like pick up the training anymore after a distribution shift was induced at 2 million time steps. Okay, I'm going to go very quickly over two approaches which we presented in the past. The first one is a bit more on the observations-based problem. So this was actually introduced by Mary, who was a PhD student in Edinburgh with whom I worked. Here the idea is basically to learn a robust embedding for reinforcement learning, right? So we basically have our encoder at the top, and this encoder is used on a standard reinforcement learning algorithm here on the right side. Now the goal is basically to make this encoder as robust to state distributions in the observation space as possible. And we do this basically by introducing an auxiliary loss. So basically we have a classifier which tries to predict if the current anchor observation correlates to the next anchor correlation. So we basically have like these tuples, like an anchor plus the anchor plus one. And then we introduce adversarial examples. So basically like the next sample could also be from a different time step, or it could be from a different episode. And the inherent assumption is here that we have a distribution shift between episodes, right? So we're trying to force a disentanglement basically in the latent embedding, which then should help the reinforcement learning process. And we basically show it works. So that's basically what the plots show. So you can see here a little bit the observational variations we introduced. So we had here a reinforcement learning algorithm which worked actually from images. On the left side you can see basically that it was mostly in blue tones, and then after the distribution shift we had only green tones. Most reinforcement learning algorithms had a drastic loss in performance and couldn't really pick up anymore. But if you equip your reinforcement learning algorithm with this auxiliary loss, then you can actually very nicely climb out of this performance loss area. Good. Second problem, and this is now more code design related. The other observation which we can make actually is that if we evolve a robot design, is that we end up with a trace, right? So of past designs and past optimal policies. Can we not use that actually also to tackle this distributional shift in the dynamics? That was basically the idea which Sergio was working on in co-adaptation with agents with self-imitation learning. So the idea was like, how can we combine self-imitation learning with reward-driven co-design? So basically we assume here actually that we have a reward function we want to optimize, but we want to make the training process more stable. And the idea is basically that we follow a very similar recipe as the previous work on co-design from imitation learning. The main difference here is just that actually our imitator is now, the demonstrator is now actually the past instances of our robot who is actually trying to learn how to walk, for example, forward, right? So we again extract a reward function from that. And the basic idea which we then introduced, and Sergio worked out actually very nicely, is that we can now combine this with the reward function given by the environment. So in this case, walking really quickly forward, for example, and then combine that with soft actor critic, for example, to combine or like to arrive at a co-design approach where we are like very quickly able to climb out of these catastrophic forgetting scenarios. So that's maybe just to show that we do first behavior learning, right? The standard behavior learning on our current prototype. Then we do the morphology optimization, basically using Q functions, which are both trained on this true reward and the imitation learning reward. Cool. And this slide, again, it basically just shows it works. Okay, if you combine reinforcement learning with self-imitation learning on co-design, you can tackle successfully the distributional shift. If you do reinforcement learning only, not so much. And then we also had an imitation learning baseline, which basically didn't use the ground truth reward, but used actually like only the demonstrations, but didn't work as well. Good. The cool thing is also like it helps really much with data efficiency, and this was like a really cool side effect which we found. So basically, especially in the bottom two tasks with the humanoid. So initially we trained the humanoid only on 1,000 episodes, like in the previous work. And then with self-imitation learning, you can actually bring this drastically down to 300. The self-imitation learning approach in yellow actually does not suffer that much performance degradation, but the normal co-adaptation approach, which uses only the ground truth reward, actually suffers from this loss in data quantity. Okay, and I make it in time, so I now can actually maybe slow down a little bit. I'm a little bit amazed. So now let's come to the second theme, which is now a little bit of a topic shift. So we're going now a little bit more into large models, right? So how can we apply and use large vision language action models, for example, in robotics? So I mean, you all know it, you all hear. So basically the current strategy in research and also like a lot of industry and companies is basically like the more data and the more parameters we have, the better the performance will be, right? And at the moment, this recipe seems to be still holding up, maybe not so long anymore, but at the moment we still see some pretty good gains from that. Okay. First, when I showed first this slide, actually, I said like the similar trend has started to arrive in robotics, but I think now it's like pretty much arrived in the last 2 years. So we had many works in robotics actually on robotic foundation models, where basically the general idea was also the more data and the more larger the model is, the more generalist you can actually train a policy, which then can train or control a lot of different robot embodiments and a lot of different tasks actually. Is that the future of robotics though? So of course, many of these methods work very well in the lab. They really work well if the computer is right next to the robot arm, or you have a really good internet connection. But in robotics, we actually have also some real-world implications. So we have latency, right? So we want to be in a low latency regime. We want to compute actions as fast as possible. And we want to also be computational efficient, right? So we do not have, or not all of our robots have like GPUs implemented. So some of our robots are really small. We want to send them out also in remote areas where they may not have connections to the network. So we also need fast and energy efficient policies, basically. And also like one good example for that is not only like small mobile robots or resource constrained robots, but of course also if you have reactive and dynamic tasks, like for example table tennis, we do not have the luxury to basically wait a couple of seconds for a larger model to basically process the data and propose an action. Okay. How can we leverage large models in robotics? How can we make them smaller? There are like usually 2 approaches which many people do. Knowledge distillation is the first one. So basically you have like a larger model which you train, for example, with reinforcement learning. And then you basically try to mimic it using a very much smaller model, which then basically uses a type of imitation learning, right? So both of these networks get the same input and need to arrive at the same output. But first you train the teacher network, then later the student network actually. Similarly, you can also do hierarchical models and contextual policies. So I think Oya actually showed a really nice extension to Octo, which was this generalist robot policy, where they actually showed that you can fine-tune these networks to like newer robots, or like basically do like last layer training on them, or even just use the embedding from these models. Then there was actually like an approach published a couple of years ago, which I found really cool, which is called hypernetworks. So if you think hypernetworks, it basically already brings up to mind hyperparameters. The idea here is really basically just that you have a network which can generate the parameters for another network, hence a hypernetwork, right? And we thought, oh, this is a really cool idea. Would it not be cool to actually have basically give an instruction to your network? For example, a binary robot has to lift the ball. Then you encode this into a latent embedding space, and you have a hypernetwork decoder which can actually produce weight parameters for a policy network, which can then actually execute the high frequency actions. So this was actually the idea of like an NWO funded project on which Arian was actually the lead postdoc. So the idea is basically on the right-hand side, we have like a high-frequency control, and on the left side, we can basically take our time and very slowly arrive at this embedding space, because the policy can work in a very fast control loop, right? Because it has only like a couple of thousand parameters. Arian actually then spent a lot of time implementing this idea in realization. So here actually is the method we proposed in Tenet, which is going to be presented outside ICHCAI in a couple of weeks. So the main training regime is basically like very much imitation learning inspired. So we basically assume that we have like a given policy where we then basically generate the actions, right? So that we have actually an imitation loss here on the right-hand side. Then for the training of the hypernetwork, we basically use 2 embeddings. So we use basically in state, action, next state, reward, so a trajectory embedding. And we combined that with a text embedding. So we basically found that using like a grounding loss to match these 2 actually was really nice to arrive at a method which can later use only text. Then we train a hypernetwork, which then produces the wake parameters for our policy. At inference time, we can basically like use only like the text embedding, right? So we basically take our textual instruction, which can vary, of course. We embed this into like the latent embedding space with using a pre-trained LLM, where we only trained the last 3 layers. And then our hypernetwork can basically generate policies which can then solve tasks, for example, like by taking the cup and placing it somewhere completely autonomously, and you do not have to query the left side actually of the larger model at all. Cool. The results show, okay, it works. You can believe me that. The actually interesting result is actually the table in the paper, which people, or the reviewers really liked, is that basically we compared to prompt decision transformers, which were relatively large, so they had millions of parameters, and we could basically show that we not only achieved the same performance, but we also arrive at a much, much smaller policy size, right? So this is the policy size. For the decision transformers, of course, you basically have to count everything. In our case, we only have to count the policy, because that's actually the policy which is executing in the end the program. The control frequency is also super high. I mean, of course, take this with a grain of salt. This was in simulation, and I asked the postdoc to verify it like a couple times, because I was a little bit surprised that we achieved 9,300 hertz. But this is because we basically have like so small numbers of parameters here. Okay. With that, I'm at the end of my talk. I thank also my team, with whom we actually went to ICRA like a couple days ago. So there's a picture of the postdocs and the PhD students. But of course, all of this work would not be possible with a lot of good collaborators and former colleagues as well. Thank you so much.
Do we have time for some questions?
Thanks for the really nice talk. I have a few questions, but maybe the nicest one is you showed at some point that you were optimizing morphologies for different tasks, like running and kicking a ball. And these became quite different morphologies.
Ah, yeah.
Is it possible to optimize one that for multiple tasks at the same time, so that you have a very general robot?
Yeah, that's possible. I mean, you need to just do the usual balancing, right? So like some of the issues you have, I mean, the normal multitask reinforcement learning problem, right? That some tasks have different scalings of the reward functions, so you need to be a little bit careful with that. In principle, that's possible. Yeah. Yeah.
Then one more. You touched also a bit on balancing between updating different morphologies and updating your policy with one morphology, and how many time you spend on each. When you're becoming very efficient with self-imitation learning, you're able to do more updated morphologies in the same time, so to say. Can you touch upon like how do you balance the time spent in RL policy learning and in updating morphologies?
Yeah, that's a really good point. If you ask me to be truly honest, I think like the behavior learning is much cheaper than the morphology production, right? If we take a look basically from the real world, right? So there is still a sim-to-real gap on the simulator. So unfortunately, a lot of the co-design papers often only show like one prototype in the end in the real world. But there's no good studies in most papers actually if the ordering holds, right? Is the best design found in simulation still the best design in simulation versus the worst design? So there are some papers where actually the ordering inverts. In that sense, for the simulation-driven work, actually reducing the number of episodes is more interesting. But for the real world, then actually it's more interesting to reduce the number of morphologies produced, right? So there's like a trade-off. So like here for simulation, that makes sense. In the real world, you actually want to spend more time maybe on the robot. I mean, the good thing is like with the self-imitation, then you arrive faster at good policies. So you maybe save a couple of hours in the real world for the training process overall. But if you compare to the manufacturing, it's a little bit more like the much more smaller component. Yeah.
Thanks.
Any other question?
Thank you for the talk. I have a question about the hyper network.
Yes.
What's your initialization of your base policy? If you have some tricks for that, or and then also are you generating the whole network, or are you generating some weights, some layers of the network? Do you know?
Ah, sorry, you mean, okay, so you mean the policy here on the right side, this region,
Yeah.
like not the teacher policy, okay.
Yeah.
No, I think we only followed the classical hypernetwork tricks. There is some initialization, so basically there's a smart trick for initialization, which I don't remember now from the header anymore, but it is in the paper. I can also look it up later. For the policy itself, I think we just optimized like we had parameters for a 3 or 4 layer MDP. So there was no special trick there. It was really just the weight matrix in the bias. So there are some optimization possibilities you could do there. There have been also like some other works with hypernetworks, I think, which looked a little bit into that. But you could definitely optimize that a bit more. Yeah.
Thanks.
And minimize the number of parameters, right? So that's what you're getting at. Yeah.
Maybe one more question. Yeah.
So also on this slide, the task description and training time and inference is the same here? Is that also the case?
Yeah, it's only in the image. Only in the image. Yeah.
Okay, so
yeah.
in reality, it can generalize over.
Yeah. So
more.
basically during the training time, so what's not shown here is basically we also have like a data set of different descriptions for each task or like for each demonstration, right? So we use this, I do remember that we used the standard trick basically, okay, we try to manually create a couple of descriptions and then using some online LLM basically to explode it a bit more such that you have like also a bit more text agnostic behavior actually in the inference time. Yeah, so it doesn't have to match one by one. I mean, otherwise it would be a little bit moot, I think, because also the embedding will change. So you do actually need to have like multiple different text descriptions to have like multiple different embeddings, such that the projection really makes sure that all of these different strings basically embed to the same embedding, and then you match it up to the trajectory encoder. So this was actually the problem, right? So the LLM doesn't know that different text descriptions map to the same inherent behavior and task in the real world. And that was basically something where the grounding actually helped a lot. Yeah.
Okay, thank you.
Yeah, we can wrap up now. Thank you for the great talk. It's really exciting to see so many applications of RL. So let's thank our speaker again. And finally, we come to the lunch. So we have a delicious international array of dishes prepared at the same place where the coffee corner was. So that's left upstairs. You can enjoy your lunch either in that space up here, or you can actually go out onto the terrace if you're craving some sunny weather like me. And then we'll meet back here at 2 o'clock to continue with the talk. So 2 o'clock sharp. Enjoy your lunch.
Test, test. Test, test.
Okay, ready? Okay, welcome back. Happy that not everybody left after lunch, so people came for BeNeRL, not just for the amazing lunch. Okay, so it is my pleasure to introduce our next speaker, Jens Kober. Like Carlo, Jens is also joining us from Germany, so that's very nice. And he also came to the similar event we organized 2 years ago in the same venue, so he can confirm about the consistency. Jens has recently become a full professor at the University of Stuttgart and the research team lead at Fraunhofer IPA. And before that, he was associate professor at TU Delft. That's how we also met him. He is focused. His work focuses on RL, imitation learning, interactive learning, and motor skill learning. So I think we can look forward to a very interesting talk. Okay, might then the stage to Jens.
Thanks a lot. We already had some robotics-related talks in the morning. I'm pretty sure mine is going to be even more applied and domain-specific. I titled it Robot Reinforcement Learning with a Little Help. As you all know, if you do reinforcement learning, especially with a sparse reward, it's literally like searching for a needle in a haystack. And at least me, it took quite some time to actually find the needle, even with this very zoomed-in version. And I'd argue that gets even worse if you're working with robots. Like we heard in the first talk this morning, if you want to do reinforcement learning on a real robot in the real world, then yeah, you need something like that on the left. That's from Google DeepMind. So it's an enormous resource you need there you can also see that they automated the resets, because otherwise you have people that need to jump in and reset everything once in a while. And you also need to make sure that the robot doesn't damage itself or its environment, or even worse, harm any people. So it's impressive that you can do that, but in many cases that's just not feasible. And then the big other alternative, and some people already talked about that in the morning as well, is trying to use simulations and then learn massively parallel in simulation and then try to transfer that to the real world. But also there you can see the millions and millions of robots that are learning in parallel. So especially in a sparse setting, it's very inefficient. So can we do better? Can't we give our little robot a little help? And in this talk, I'm going to talk about roughly 3 different types of things we've been looking at. Kevin in the morning was talking about actually also making use of embodiments, and there's probably a few more. So let's start with the more classical one, a little help from better simulations. If you want to do sim to real, you have to trade off between usually kind of how robust it is and the performance you get. So if you what you usually need to do is some kind of randomization. So you randomize some parameters of your simulation in order to make the policy robust, and hopefully the real world is kind of in distribution of what you have seen in simulation, and then it's going to work there as well. But if you randomize too much, then it's going to be very robust, which it comes at a loss of performance. So it's important to minimize the model mismatch, and even then you need to really be aware that effectively all models are wrong. So the goal really is to try to mitigate the relevant mismatches. And there's quite a lot of tools for that. Isaac Lab is probably the most famous one, and we already saw a little video clip of that. Some based on game engines, which for most cases focus more on the visual appearance and on physical accuracy, and there's many, many more. So why is all this mismatch important? I'm going to show you a few examples of common pitfalls. So the very classical one here, the inaccuracies in simulated dynamics. I'm going to use this very simple pendulum swing up, or equivalently a weight on a disk as a running example. And then what you see at the bottom always in red is the performance. Also, in this case, to make things confusing, it's a cost and not a reward. So lower is better in red in simulation, and then blue in reality. So if you have an inaccurate model, it works perfectly well in simulation. That's the little video clip on the left. And then if you just transfer that to the real world, then it performs significantly worse. And you can mitigate that by using domain randomization. Then you pay here a little price in simulation, but the transfer works a lot better, and the performance in reality is quite a lot better. So that's the very well-known one. But there's more. You can also unknowingly change the Markov decision process, or the Markov property. So one example we came up here with is we're training the robot to push the little block to the position, the transparent position. So here it's trained without collision avoidance. You say, okay, in simulation I can simplify my life, let's just train it and not care about self-collisions and collisions with the ground and so forth. But then if you transfer that, it just doesn't work that well. So there you try to make your life easier, but actually change the properties of the problem, and then the policy doesn't work any longer. And here is kind of the equivalent, but now trained, actually also having these safety properties of the robot in the simulation. Another important thing is delays. In simulation, everything is more or less instantaneous. If you have a real robot, a camera image comes in that has some delay, you send out a command, and then lower level motor controller and so forth. So you're going to get some delay. And then again, even in this very simple system, you get crazy stuff like this. So also there, if you include it in the simulation, that works a lot better. And then one final thing, Also, in robots, you have many, many different components. You have your cameras and other sensors. You have your actuators. You maybe have some neural network that does some pre-processing and whatever. They run at different frame rates. They might not even have deterministic frame rates. So quite often, it's actually asynchronous. And also there, if you don't take that into account, it won't transfer well. The very first one with the mismatch in dynamics, that's something that is very well covered in most of the standard kind of tools you have. The others, not so much. Two of my PhD students, former PhD students, came up with a new framework that's based on Python 3 and compatible with the gymnasium environments, where you can really model all those things and very easily switch directly from simulation to the real world. And effectively what you do is swap out one of those blocks between the simulated one and the real one. And then you can do fun stuff like this, where you can take a look at the modules, and we also see an example of, again, a block pushing one. And here we actually had two different robots, so the spots that we control walking around, and then the tiny little quadcopter that is supposed to land on the platform, synchronizing all those, and also having the sensing in the loop with all the delays and asynchronous stuff. And also here another example on applying that to a simulated assembly task and some kind of a motor engine kind of thing. So that was all mostly about being able to actually simulate all those things. And then in a follow-up work, Bas worked on actually using the graph structure and being able to propagate through all that to actually also identify, in this case, the delays that are present, and then using that to refine the reinforcement learning. And here, that's a drone flying in a scene from the top, flying in a circle. On the left, properly simulating the delays. On the right, not, and it's just starting to drift out and do crazy stuff. So taking these kind of things into account, the knowledge you have about the system and properly integrating it into the simulation to get better simulations really, really helps a robot to learn better and faster. Kevin talked about their use of LLMs. I'm going to give a slightly different way of using them. So for them, you had the hypernetworks, and then kind of on the lower level, a neural network that does the actual states to actions. Typically, you wouldn't use directly a foundation model on LLM to pull it at a couple of 100 hertz and do the control in real time. So you need to find some kind of way to have an intermediate representation. Here, I'm going to talk about a different kind of representation we use. So here, what we use is called code as policy. So effectively, the LLM generates a little Python program that could be something like move to position X, Y, Z, and then that gets executed and serves as policy rather than telling you having a lookup table more or less for which action you're supposed to take for every state. So our idea was to use LLMs to help reinforcement learning in exploration. So they're good at common sense of reasoning, but at least the text-based ones typically don't know much about the specific hardware and the physics. While reinforcement learning, like I was saying in the beginning, tends to struggle with large observation action spaces before it can discover something useful, but by learning from interactions with the real world can really counteract these inaccuracies in the foundation models. So how that looks like is we have a user command that could be whatever, put the yellow block in the yellow container. We have here a vision language model that we use to pre-process it and crop out some of the things. And then we use the language model to provide the base policy. And on top of that, we have residual reinforcement learning, so learning the offsets from what the LLM tells us to fine-tune it. So you get here the base action and then literally add the offset to that. A bit more in detail, so like I was already saying, you have a command. We have here the image crops, and then from that you also get at least the center positions of those objects. So that's all in 2D and seen from top. And then we still need to figure out exactly where you want to grasp it. So for the bowl, maybe you can't grasp it in the center, but need to go to the side or something like that. And then the residuals are the offsets relative to the center. You probably can't read that, but we provide quite a lot of structure in the prompts on how the scene looks like, what the objects could be, how the code should look like, and these kind of things. And then also here we use code to generate kind of different possibilities for exploration where you should try different pick locations. And that's based on OpenCV, a computer graphics library, computer vision library, sorry. So then you can try different things. So we tried both kind of just pick one place. That's the thing you see on the top here. And we actually mix standard random exploration in reinforcement learning with the LLM guided one. And then obviously you need to decide on the percentage between those two. So the dashed line on top, that's the best you can get purely from an LLM. And then here, the blue one is 0% LLM, so that's just regular reinforcement learning like exploration. And then the orange one is mixing in 20% of this guided exploration. So you can see that it learns significantly faster and also does a bit better in the end. The picture completely changes for the bottom plot, where the task is to put all letters in the bowl of the same color. It's not just a single step, but quite a few steps. And they're using only reinforcement learning without the guidance, at least for the number of steps we tried, didn't converge at all. Because we have quite a lot of structure in there, and using this code, it also allows us to do zero shots, so without any further fine-tuning, transfer to a real robot, both for short horizon and long horizon tasks. So here's two examples of that, just for a single pick and place. So this work was kind of restricted to 2D, just pick and place location, and like I was saying, pick and place. But usual tasks are a bit more complex and interesting. So this follow-up is in 3D, so you can actually move objects around. And we also looked into different possibilities of doing picks and places. So also there we use LLMs at multiple levels to come up with kind of the general high-level plan of which steps you need to take. And then the middle one here is deciding on, for example, if you want to pick this little box here from the side or from the top, and then the goal is to put it in this shelf here. And if you kind of look at this one on the bottom, you can probably tell that if you grasp it from the top, you won't have enough space to put it in the shelf. So that won't work in this case, this variant of picking. But that's something that the text-based LLM can't really reason about. So here that's going to influence, so that's why we need also the reinforcement learning part. So what it does here is we again have some kind of a base policy, which you see in dashed red here. So that's just straight lines to the object, and here the policies are effectively a little function parameterized by where the goal position is. And then what it learns are those offsets to give you the nicer shape here in blue. But it also feeds back by figuring out what works and what doesn't in the in the higher level reasoning of the LLM about which of the two options it should pick. So should it pick the box from the side or from the top? And we do that by estimating both the value function for these two different variants of picking, as well as the uncertainty. So you can see here, in this case, pick the box from the side, has a lot higher value and lower uncertainty compared to picking the box from the top, which just doesn't succeed when then continuing with the sequence and a lot higher uncertainty. And that then plays, so then effectively this gets fed back to the LLM and it knows here when deciding between those two, which one it shouldn't take. We tried on 6 different tasks, and then most of those based on states. These 2 of them also based on camera inputs. Here, again, the blue and orange lines are our approach. We tried with off-policy and on-policy reinforcement learning in the background, and then here a few other baselines. One set is starting with demonstrations and using imitation learning, behavioral cloning to warm start the reinforcement learning. That's the dashed blue and orange ones. There's also other approaches that use an LLM to generate a dense reward from a sparse reward. So it's called text to reward. So you give a description and it tries to shape the reward and another baseline. And you can see that overall they work a lot faster and also get higher final performance. And also here we managed to do a sim-to-real transfer. Exactly the problem I was using as a running example, picking up the box, and where you need to pick it up from the side to put it on the shelf. And this is in real time. So to the last kind of help I wanted to talk about is help from humans. So this kind of idea of interactive learning, as Giacomo also mentioned in the introduction. A long time ago, I worked on ball in a cup, just using reinforcement learning. So the goal is to catch the little ball in the cup, takes some 35 times. There we helped by warm starting it, providing an initial demonstration. If you just play that back, kind of does it, but doesn't really work that well. And then you start fine-tuning it with reinforcement learning. So that's policy search, actor-only reinforcement learning. It takes some 40, 50 trials to get it in sometimes, and then 100 or so to converge. So what I wanted to really look into, and what we looked into the last 10 years, is can you do better by actually actively having a teacher in the loop? So something like this, you have the classical loop with states and actions and the policy on the top, and then you have a teacher in the center who can observe the states and actions and then provide some kind of corrections. And we actually also have a poster on a similar approach up there if you want to know more. That's more on the imitation learning side. So there you can have different types of interactions and corrections. So here we used offsets effectively that you get from the teacher rather than the absolute actions. And how we modeled that is using a policy search approach, and rather than just having the standard perturbations as exploration, we also have the possibility to have a human teacher provide corrections, which then are a different form of exploration. And then you can use any standard policy search approach in the background. I suppose many of you are familiar with actor-only approaches policy search. So you have some current policy on top here. You do a number of rollouts with that, with some exploration on top. So you try out a few variants, you evaluate the reward or cost for each, and then you update the policy. And now if you make that interactive, rather than having here the random exploration, we also give a person the possibility to jump in and correct. And then we switch off the random exploration, as that tends to get a bit confusing for people if the robot does random stuff in parallel. So same problem here. Now we can actually start from zero, so without any initial demonstration. And what you can see is Carlos, my former postdoc, sitting in front of the robot and providing those corrections, like moving more to the right, moving more to the left, or something like that. And then after some 20 trials or so, it can catch the ball in the cup. Doesn't look that different if you start from an initial demonstration. So in red, we have the policy search, which is the pure reinforcement learning. Again, cost, so lower is better. And here the number of times, the number of rollouts, we try to catch the ball in the cup. In green is using only imitation learning, where you're pretty quick, but then at some point you hit the limits of the human teacher and it levels off. And combining the two of them, you get the best of both worlds. So you learn very quickly, but then even get a better final performance in the end. And then the picture changes quite a bit if you now start from scratch. So without an initial demonstration to warm start the whole thing, then doing reinforcement learning takes some 200, 300 trials, while with the interactive approaches, you can still get down to 20 or so trials. So that really shows how a human can help and how it plays to the respective strength of a human teacher and the robot. Robots are pretty good at doing stuff reproducibly and fine-tuning, while a human teacher is good at getting the high-level strategy and exploring and getting the robot in the right direction and right region of the policy. How we set it up here, that obviously comes with one major downside. Let me just try to go back. So everything for the update is based on the evaluation of the cost. So that's the robot cost. So that means this only works nicely if the goals of the human and the robot are aligned. They try to optimize for the same thing. We also did some work on interactive reinforcement learning. That works well for fairly simple tasks, but unfortunately didn't scale too well. So to sum up, as you all know, sparse rewards are challenging. I presented a few different ideas on how we can help robots to learn quickly by providing better simulations, using the general knowledge encoded in LLMs, doing warm starts, or having humans involved more actively during the learning process, and there's many, many more. At least for the last 3 here, that comes at a cost. You learn a lot faster by limiting the search space, but obviously also you won't be able to find the global optimum any longer. With that, I'd like to thank all of you for listening. Here, somewhat dated picture of my group and some other people that contributed to the fun work I had the pleasure to present today. And that's the 2 projects that mainly contributed to the work. Thank you.
Thank you so much. We have time for a couple of questions.
Thank you for the really interesting talk. There was one figure that you were showing with the robot trying to put the letters in the box, and
yes.
There were 2 graphs associated with that. And then the second graph you said it didn't really converge.
Yeah, sorry.
That's okay.
Come on. This one?
Yes. Here in the second graph, there's a spike after 30,000 steps. Like it's the blue and the yellow curves are pretty similar, and then there's a sudden spike. What is like? Did you investigate? What was a possible reason for this?
So you mean let me try to find. So here, when it suddenly starts to go up.
Yeah, like why exactly after 30,000 steps?
I'm pretty sure that's just a coincidence. It's not a magic number that something changed in the task. And what I mean by not converge is here the blue one, so the one that just uses random exploration.
Yeah, that's what I was trying to understand. Like one of them suddenly goes to convergence, so why that could be the case, but okay, thank you.
Yeah, sorry. Code is available if you want to play with it.
Other questions?
Hi, thanks a lot for your interesting talk. Actually, it's about the same slide, this question. Intuitively, it seems very unclear to me. Why does this LLM help in exploration? Maybe this is not known, or maybe this is obvious, but why would this help?
So what you see here in the black dashed line, that's what would happen if you use only the LLM. So the the policy that the LLM spits out is okay-ish, but not perfect. So and it works for some cases, but then fails for some others. So it's again a form of warm starting the reinforcement learning process.
Okay. Yeah, thanks a lot.
Maybe one final question, if somebody has any. Yeah.
Thanks for the talk. I was wondering about these corrections that you were doing with the human. Are these similar to imitation learn, or how are these corrections actually encoded into the data?
Yeah. No, I don't have a good slide on that, I'm afraid. So we tried out a whole lot of different things, and there's a whole lot of different ways you can do it. The feedback could be just binary success failure, which is like a human-generated reward in a sense, or some other, or maybe a more fine-grained reward. It could be the absolute action. In the example I showed you here, it's a correction, so it's an offset on the action, so it's more a gradient. You should move more to the left, but not necessarily to the absolute position. It partially depends on the type of task you do and what works best. In the end, it gets mapped to a new action in some form. So in that sense, it's similar to imitation learning.
So let's thank our speaker again. I would like to invite our final speaker of the day to set up. So our speaker is Yulia Olkhovskaya. She's an assistant professor at TU Delft. Before that, she was a postdoc at Vrije Universiteit Amsterdam and got her PhD at Universiteit Pompeu Fabra. She works on designing and analyzing algorithms for sequential decision-making, focusing on bandit problems and theoretical reinforcement learning. So I guess from the title of the talk that she'll tell us all about that in great detail. So Yulia, the floor is yours.
Thank you.
Yeah, you can use that one. Yeah.
Okay, thanks a lot for introduction, and thanks a lot for staying for the last talk of the day. It was a long day. So I'm really glad that at the previous talk some problems with sparsity has been mentioned. And this talk, it will be quite different kind of sparsity, but yeah, we'll look at that soon. So this work is based on joint work with Hamish Floon from Universitat Pompeu Fabra and Paul from Polytechnic University of Catalonia. And at this talk, I will talk about contextual bandits. So let's first describe what is that. I will use the example of the advertisement placement. So imagine that you want to design a system where you want to show different advertisement to every user entering your website. And then in the beginning, you don't know anything about the preferences of the user, about the nature of the advertisement you're using. And then your system is repeatedly doing the following. So first, the website is visited by a user. And for the user, you observe some features. It could be some profile details, location, other things. And then the website is choosing the advertisement to present to this user. And then it wants to see how well, how good was this choice, and how can you decide that? You see how user responds. So it can clicks in the best way, like in the best scenario, it clicks to the advertisement that you present, or it can just leave, or maybe it clicks later. And you do it sequentially. So at each time step, you present different advertisement to the users, you update your rule, how you select the advertisement for different users. And with the time, supposedly you update your rule such that you present more relevant advertisements. So formally, the problem setup that we will look today will be the following. So for each time step, the learner observes the vector, and for different, so there was the advertisement, so for different advertisement, we'll see different vectors for each user. And then the learner selects one of the final set of actions, and then the learner observes and gains the reward, which is some function of the chosen context, plus some noise. And the overall goal of the algorithm that selects which action to choose is to minimize the cumulative regret, which is a difference between the cumulative reward that would perfect algorithm get. So if it would choose the best, let's say, advertisement, as in the previous example, to show to the user, comparing to the actual reward that was obtained during n steps. So this problem setting, it's definitely simpler than ones from that considered for reinforcement learning, but you can also think about it that if you study that this setup can be further extended to your more complicated task in reinforcement learning. So we study first this setup to understand what is the limitation of the learning algorithms, so how fast we can learn and what formal guarantees we can preserve. But further, of course, if you get the some results for this setup, you can extend it to reinforcement learning algorithms. But also, even in this setup, it's not interesting only because you can study it theoretically, but it has some actual applications. So the first I mentioned, that's the advertisement placement. For example, it can be also used in website optimization. So you want to decide which version of the website you show to which group of users. Also, it has been used in clinical trials to make some more adaptive tests than just A/B tests. And there, the arms would be possible medications, and the context would be patient symptoms, and the reward would be the health outcomes. How did this medication work? Right? So let's now move more particularly to the definition of the reward that we use here. So first, the most simple definition of the reward we can consider is just a linear reward. So you observe the context for, so here the current context for action AT, and then your reward could be just a linear function of this context that you observe. Then what you could do, you could sequentially learn this parameter theta and learn the rule that selects the optimal action based on the learned theta. But I promised you some sparsity in this talk, that was also in the title. And for the linear reward, we could easily define the sparsity, right? We can have just some feature relevant to us, some are not. So for example, as in the first example I gave you, you may have features about like maybe some location-based feature may be non-relevant to you, but the age or the cookies of the browser could be more relevant. So you perhaps sequentially can, so then you sequentially can select which features you use. But then, of course, it's hard to model. The world is more complicated, so we cannot just use the linear features everywhere. And the nonlinear structure has been also studying broadly. So it has been some non-parametric methods from statistics has been adapted for this bandit online setup. Also work on wide neural networks. But then the question is, how do we define formally the sparsity for this setting? And in this work, we actually make the first attempt to study how can we select the relevant feature functions in such setups as wide neural networks and non-parametric functions. So we study two notions of sparsities. So you don't need to look, it's like, it is the last talk, so you don't maybe need to look at all the formulas, but most importantly, we assume for this kind of sparsity that we have, that our reward function can be written as an infinite dimensional linear function for some particular feature map. And examples where you can see it, it's learning with kernels methods that you saw in machine learning. And but here we'll consider the sparse case. So what the sparsity means here is that only from this infinite set of candidate features, only finite set S of them is relevant. But then the question is, how do you select only S of them from the infinite candidates of features? So the first method that we present will deal with this setup. And the other setup is how can you define or could define a sparsity for a nonlinear case is the following. So it's again the infinite dimensional linear function with candidate features. But now the features are all the same function, just they have a different parameterization with some vector theta. Again, this also is used in kernel learning, but also it directly can be used to model the neural network, so particular infinite range, infinite width neural network. The sigmoid function here will be this candidate feature function with different weights. So in contextual bandits, in the theoretical study of this online learning, we care about limitations about the regret. So what is possible and what is not possible. So how regret could grow with the number of steps. And for this particular setup, we have shown that basically it is not possible to obtain the regret less than what is shown here. So basically, if you have n type steps over which you run your learning algorithm, there is always will be the environment where you gain that much regret. So it will be square root in the number of time steps you have. It will be also depend on the square root on the number of actions your model had, and also depends on this way as a square root of candidate features you used. And similar rate there is for the uncountable sparsity. I will not load you that much with the detail here. And also, okay, so we talked about the lower bounds, but what can we say about the upper bounds? So what can we prove here? So to prove the upper bounds, we need to provide some algorithm for which we can show that this algorithm does not get regret more than some particular quantity. So ideally matching the lower bound. This is this is how it's often studied in this field. And the algorithm that we use here is some variation of the Thompson sampling algorithm that you probably saw in the reinforcement learning courses. But for this Thompson sampling algorithm, we define the loss function as following. So let's say normally in the Thompson sampling algorithm, you have some, you compute some posterior over the parameters of your functions. And here how we define the posterior for the set of functions that I just defined to use is sparse non-parametric functions. So we have some, so we describe all our parameters as V. And to define the posterior, we just have the square loss between the reward that function with those parameters will gain and comparing to the true reward that it gained at that point for that actions and context. And we also add some penalization for this candidate of the parameters. And then we just use the Gaussian form of posterior with this loss function, and then we select the parameters of a function from this distribution. So it has more specification for each type of sparsity, but the most important to see from here is that this is a variant of the Thompson sampling adapted to that particular problem. And so here some fundamental limit exists because it's quite hard to define what kind of posterior we'll use for that kind for these nonlinear functions. Because first, you remember there was like infinite number of candidates of the features, and we need to select just finite number of them. So first we need to select how many of them we need, and then which one we use. So this is how we simply construct the posterior. So it's all big formulas, but just like this part uniformly selects the candidate, like the number of candidate features that we use, and then it allocates it just chooses which set of size M we use to allocate the features. And then for the choice of the weights, we again choose them uniformly in some small balls there. The problem is that it's not computationally efficient to sample from the posterior corresponding to this prior, but I will leave this discussion further why this is still interesting and how can we approximate those methods. And then, luckily for this type of prior that Thompson sampling uses, we can show almost nearly matching upper bound. Okay, I will skip these details, but in similar flavor of defining the prior can be defined for other type of sparsity. And also there is a nearly matching, the upper bound that nearly matches the lower bound. To compare to the previous results, first I introduced you the linear bandit, so when we just have a linear reward function. And with this method, comparing to the previous results, we managed to move the full dimension, so the full dimension of the reward function. So it was the square root of the full dimension, and now it is just logarithmic. So we have managed to improve it by moving it from polynomial to logarithmic. And then for the kernelized setups, the improvement is the same. But of course, the price is computational efficiency. So first of all, this method that I used before, like so this prior that I have defined, you remember this, like there was this huge formula. It's actually used a lot in statistics as well, and in the regression methods, it's called the spike and slab prior. And there has been several works that show there's that MCMC method can approximate it quite well. But unfortunately, we don't no, like how well, there's no formal guarantees that show that, yeah, you can approximate it up to some error and what the rate of the error will be depending on how number of simulations you use. But this is quite a fundamental limit here. And the problem is that, we could use maybe some other methods. And there are some methods that allows to reduce the bandit algorithm, the regression oracle. So, you know, you have like a lot of methods for the regression, and perhaps something exists there so that we can adapt. But unfortunately, no. So even just for online linear regression, there has been shown the fundamental trade-off that it actually has been shown that you want to have a polynomially run algorithm. You cannot achieve that fast rate for the sparsity rewards. So this is, this computational efficiency doesn't come for free. But still, how can we make it computationally efficient? Because, yeah, the sparse reward, as you saw, it also appears in reinforcement learning. So you can, you want to use these models, right? You want to use the neural networks. You want to use a sparse reward. So yeah, we want to get at least something theoretically grounded for that. And yeah, that can achieved, but by lifting some assumptions. First, we need to assume that the contact distributions is IID or nearly IID. Plus, there has to be done some assumptions that also appears in just in online regression, that the covariance matrix should be well defined in all directions. So it should be not that sparse. And yeah, to sum up, in this work, we study the limits of how can we exploit the sparsity structure on the nonlinear models in contextual bandits. And we show that we can get big gains if you have small number of actions and if we allow our algorithm be not that computationally efficient. But there are a lot of open questions. So first, if you maybe relax some of the assumptions, if you allow the context to be IID and we assume some assumptions about the contact distribution, is it possible to get some regret bounds and simultaneously get computationally efficient algorithm? And there are many more related open problems. So what if you have some limited feature observations? How can this propagate to the nonlinear reward functions? So I feel that this area of learning with sparse rewards in online setup is underexplored. So there are many more open questions. I will be happy to talk about them offline. Yeah, thanks a lot. But, that's all.
Any questions? Yeah.
Thank you for the presentation. My question concerns, I'm interested in knowing, for example, when you talked about specifying kernel bandits, let's say we select S features from infinite dimensional feature space. So I am curious as to how the regret bound of that setup compared to, for example, we just simply approximate kernel methods with like S random features or something like that.
But then if you just approximate with them with random features, there will be some mismatch, right? There will be some model misspecification that you gain because the model that you use is not correct. So then this model mismatch, like in the regret bound, it will just propagate linearly. So we'll have additional term in the regret bound. Let me show just any regret bound. Yeah. So you'll have additional term. So let's say you mismatches like epsilon. So at each time step you have like epsilon error that you gain. So this will just have additional term that scales with the mismatch that you accumulate over t time steps. So there will be linear regret in the number of steps that algorithm does.
Okay, and perhaps a very quick other question is, do you see ways of extending the setup to, for example, infinite action spaces?
Yeah, good question. So, yeah, for this particular setup, perhaps the assumptions on additional assumptions of contact distribution could help, because then we could use a different regression method. Because in the current assumption, we just assume that context can be generated arbitrarily. So there could be even some someone from outside that give us on purpose the bad context vectors. So if I assume that it's generated ID, yes, there could be some other more efficient methods to, that will work in this setup.
Any other questions? All right, then we move to the coffee break in the usual spot upstairs, and we meet back here in an hour for the final panel and closure of today's workshop.
can start. Is also. Okay, we are going to start in 1 or 2 minutes, okay? Fixing one thing. Okay, so we now begin the last part of BeNeRL. So what we had in mind is some kind of a semi-unstructured panel discussion. So we're going to start with a question for the speakers. Then each speaker will give a short answer, after which we're going to continue with questions from the public. When you think of a question, please think of question that all speakers can give their input to. Okay, so we can start some discussion. And the first question I want to start the panel with is we saw a lot of progress in terms of applications in deep reinforcement learning, VLAs and robotics. That's my field, that's why I know it in particular. But we saw that this technology has had a lot of impact in the last 10 years. And of course, all of this comes from fundamental RL research that enables this kind of technology. So my question for you is, what do you think is the biggest, are the biggest missing things in RL theory or in RL methods that will be most beneficial for future applications, for example, in deep reinforcement learning or in, just applications? Okay.
Yeah, for me, I don't know if it's a personal thing because I like to work on that, or if that's maybe someone else also shares that opinion, but working with a large state space, I think that's quite a big deal, and there is not that much fundamental result on the setup like that when you just want to extend it beyond the tabular MDPs. Yeah, for me, there has been some progress in fundamental RL on that, but again, under quite some limiting assumptions. And I see a lot of open problems in fundamental research on that. Like maybe what I touched in my talks, like there are a lot of results now obtained for linear settings, but in practice we'll use neural networks and complicated models. And then how can we get formal guarantees for large state spaces? That's quite a big question.
So if, I think for me also, I work on offline RL. I think what is missing for RL to do research is good enough data. So usually, yeah, we know that RL is data hungry, and then it's not like LLMs that we have access to a lot of like available text or other data sets. It's difficult to train RL when we have not good enough data, so I don't know. And the data sets that we have usually is not in the format of like this sequential decision making. So if you want to address really the real problems, like in healthcare, in fairness, in like the social problem or anything, so it's very difficult to train RL methods when we don't have the data. And the simulation is also difficult. So maybe in robotics and some other games, we can build simulators, but in many applications, we don't have that. So that should be something, I don't know how to solve it.
Cool. Maybe to name a couple of things or like a couple of open problems to work on which haven't been mentioned yet. I think learning to learn, like meta learning, I think is super interesting. Like how do we learn actually how our reinforcement learning algorithms can solve future problems. Data has been mentioned, right? So data is super important in robotics, of course. I think handling uncertainty or like new data modalities is also probably an important field. But then I think also like co-design is actually like a super interesting case, right? So I think like reinforcement learning plus X, right? So like some other method which is basically fused with the standard reinforcement learning setup is like super interesting. When I started working on co-design, I think there were 2 or 3 papers which actually used reinforcement learning with co-design. I think this time around, if I go to ICRA or IROS, there's like the robotics conferences, there's like always like 3 or 4 papers about co-design these days. So I think that area is now taking off really. And I'm pretty sure there are like still some other problems out there where reinforcement learning could actually help to solve the problem, but we don't yet have the fundamental theoretical framework, right?
Lots of things have already been mentioned. I'm not sure if it's a question for more fundamental reinforcement learning research. I would argue that reinforcement learning, if you go to slightly more complex problems, still is extremely brittle. We have come up with a few good, I don't know what to call them, hacks to make things work. But in general, kind of predicting what's going to work and what's not going to work, and if it's going to converge and how quickly, and which tricks we actually need to apply or not. That makes it that reinforcement learning or applying reinforcement learning often is still more an art than a science. And if we could get some more structured and fundamental insights on how to then tackle real problems, that would be awesome.
Okay, so I think data is never enough, right? We always like data and to add more information to our model. But I think we can say already that we have a good amount of data, and what we miss is actually the ability to generalize a bit more. So from what I see in deep reinforcement learning, we are really struggling to avoid overfitting and to make the model able to understand how to distinguish tasks, how to interpret them, and how to kind of leverage the similarities in order to have better skills, more generalization, and so on. So I think data might reach soon a kind of wall at some point, and we will face again the challenges of making learning algorithms powerful, more robust, and more able to generalize. I think we are already starting to see something similar, because if you think about LLMs, even in models like ChatGPT, Claude, and so on, there are so many hard-coded parts already that to me make me think that they are already starting to, face a kind of challenge that we will have to overcome at some point. So the challenge of really understanding tasks, understanding problems, and trying to leverage this understanding to obtain better models.
Okay, thank you very much. We can do some questions from the public. Yep.
Thank you for all your comments. Like you mentioned in the end about generalizability and making models learn more skills and not overfit, what are some ways that we can try and move towards that and have general models for robotics, for example, that transfer, or any other transferable models?
So I like very much the whole direction of multitask learning, transfer learning, meta learning, and so on, as also Kevin mentioned before. I think a nice future direction to investigate is definitely learning to learn. In particular, I'm seeing some works now on how to learn reinforcement learning algorithms, how to basically go to the fundamental meaning of learning. And I think this can be some future direction that we should explore. Even, let's say, the work I presented before, the parameterized Bellman operator, it's a kind of way to understand how learning works. So I like to go toward this direction, and I think this will need to be faced at some point if we want to make real progress in reinforcement learning and machine learning in general.
You mentioned basically general policies, right? So I think that's like an area of research which is worked on right now. I think I have seen like a couple of examples actually this year where people are training general policies for multiple environments and to some extent for different tasks. I think the biggest challenge there, I mean, these papers look really impressive and they claim they work really well. But they're not yet actually working on tasks which actually matter in the real world. So I think there's like a lot of gaps still there, right? Like if you actually look a little bit beyond just learning a policy for all possible robots which actually have to do locomotion, right? Locomotion is somewhat, some people say it's solved. I mean, there's still probably something to research on. But general locomotion is also like not the most exciting result. Like manipulation, for example, right? That's really tricky, or different objects. Yeah, and then a lot of this research actually is driven by availability of data. So a lot of this work actually is only done in simulation and then transferred to the real world. And I think there's a lot of space where you can ask questions actually, okay, where does the sim to real recipe doesn't work, right? So there are definitely areas in robotics where we don't have a good idea about the environment. I think my most favorite example is always like, if you build robots here for Earth, okay, this works all well. If you send them to another planet, what happens then, right? Like the Curiosity rover, I think NASA figured out after they sent up the latest rover that they need to redesign the wheels, for example, right? Because the wheels are not really robust to the rugged surface of the Mars. And if you think like there are people on Earth who should know about it, it's probably like the people at NASA, right? But even they couldn't expect that. So I think a lot of these problems are really, really interesting to look into.
Yeah, also, it would be nice to see like what are the limits of the generalizability, because you'll need, indeed, a lot of training data. So you cannot cover all possible environments when you train. So, yeah, perhaps, we wanted to generalize more, but we should understand that there are quite a lot of limits on that.
I would argue that to achieve that, you actually need to go quite a bit beyond pure reinforcement learning. I mean, they were mentioning data already, that you can use more kind of in a supervised way to get that in, or other forms of prior knowledge. And then like Julia was just saying, just determining what you want, what makes sense in terms of generalization. Yes, theoretically you could generalize to everything, but that makes it an infinite space almost. So kind of where to draw the boundaries, that's one big question that still needs to be answered.
Yeah, I don't have much to add, but I think there have been some work done on like different generalization tasks. So I also presented a little bit of like cross-domain generalization. So we should look for some things that we can find a common representation space for the state and action or something, a class of tasks. When we were working on that cross-domain generalization, so there are many different ways to define domains, tasks, environments. So it's been difficult. So we defined it like if just the transition function changes or it was the same everything. So a bit of difference in the probabilities. So I think there is no big work like the other domains that the transfer learning is as easy as those. I wouldn't say easy, but like similar to those work that has been done. But I think progress could be made based on like in different, how we define this generalization and yeah, in what sense, like you said, we want to do that.
Great. I think that was a very relevant question for everybody, and also great comments by our speakers. I like the idea that you mentioned about investigating representation and how that fits into the whole system capabilities. Are there any other questions that people would like to ask? Yeah.
Thank you for the answers. Do you think scaling neural networks will play a big role in the future for reinforcement learning, similar to how it was in computer vision or NLP?
So I didn't get the questions.
If scaling is going to be super important in reinforcement learning in the future.
It's going to improve. Okay. I think we tested that. so when we were working in this offline methods, we tried, I'm not sure with the scaling, so there was this concept of very deep neural networks. And we couldn't get the results, so I don't know. So maybe somebody else has a better intuition on that.
So I think scaling makes sense as long as you do something meaningful, for example, adding convolutional layers if you are using image processing techniques. So if the input is an image, you need convolutions. In general, I think more than scaling, we need something that adds structure to your neural network. So you need always to understand which kind of input you are considering and then model your neural network architecture based on that. We have seen also during my postdoc, there were some colleagues working on this model called deep Lagrangian network. They were basically trying to inject inside the neural network architecture some Lagrangian dynamics. And they were using it for learning control in robotic applications. I'm pretty sure nothing could have been achieved by adding layers randomly so nice like they have been able to achieve by doing something more thoughtful, like adding structure in the network. So I think more than scaling, we need always to understand what we are doing and how to do it in the best way in terms of structure.
So I think the question was like, is scaling important? Like, was it like also in the direction of, is it like a worthwhile research direction or like something to look at? Okay, I see. So I think as a research direction, I think it's super interesting, right? And like a lot of people, especially industry, right? So I assume you work in academia. Industry is going in this direction. We have like in America, certain people founding startups where the whole story is basically that they collect data and train a policy to control at least one robot on a lot of different tasks. I think the idea is like really interesting, right? So like basically like the idea is that the more data you have and the more, you know, basically this OpenAI recipe, right? So like the more parameters and the more data you have, like the more general or more multitaskable the network should become. And in robotics, we have also like the embodiment, right? Although you have to take care that in a lot of these foundation models, there's a little bit trickery going on, right? So often it's only end effector control they're doing. There are only like a few examples where they actually do a low-level control. So there's still hope if you see these papers, right? They cannot solve everything at once. But I mean, there's also a concern, of course, if you as a researcher want to go into this direction, do you need to do, do you need to do or apply basically, go into the direction of scaling your networks larger and larger? And I think you said something really, really good about that, right? So like if you want to investigate these fundamental questions in reinforcement learning, like let's say safety or like how can we have our dynamics functions generalized better, I think even with small scale data sets and problems, you can still actually investigate these questions really, really well. So I see it like as more like two general streams of research, right? One is about the normal academic one. So we have ideas, we want to investigate them. And of course, our resources are limited, right? So we don't have $1 billion for a research group normally to hire a lot of people to collect the data for us. So like it's often a little bit more limited. Same with the GPU compute. But I think there are like a lot of interesting questions you can still investigate without being forced into scaling up your networks or reinforcement learning. But of course, it is an interesting question, right? So like I think the end of the road is really how can we rediscover basically our own brain, right? How can we basically have a machine which can learn by itself how to solve tasks? And we actually, the humans, like we are super data efficient, right? We don't need internet scale data to learn one task. Like my kids basically learned how to grasp objects without needing to access the internet or look at a lot of different humans, right? You just show them something and after one or a couple of tries, they can actually figure it out. So interesting, yes, worthwhile to go as well, but it's not the answer to everything, I think.
I would argue that scaling a network up only makes sense if you actually need the additional capacity you get, the learning capacity you get by scaling it up, which means that you actually need the data that comes with it. And unless we're talking about offline reinforcement learning usually means that we need to have the agent generate the data itself, which brings a big bottleneck. So maybe it would make sense if you want to learn many different tasks at the same time using reinforcement learning. Yes, then you're going to need a larger network. What Kevin was just talking about those kind of generalist robotics models, what you often see, at least nowadays, is that they use whatever you learn using reinforcement learning as just yet another data stream that you use to train those very big models in a more supervised setting. So, and if you look more into the offline reinforcement learning direction, then things start to become very blurry on is it really reinforcement learning? Is it imitation learning? Is it kind of something in between? So scaling up on its own for reinforcement learning, I wouldn't think it's worthwhile.
You had a question, right?
Yeah. Thank you again for the talks today. I was presented with some really nice insights and enjoyed all of your talks, so thank you for that. My question relates to the idea or the context of explainability. Reinforcement learning, especially unsupervised learning, can often seem like a black box where we draw empirical or anecdotal insights from. Do you think that with LLMs being slowly integrated into reinforcement learning that this helps or harms the explainability of the methods that we're trying to draw insights from?
Yeah, maybe it makes it harder to make it explainable, right? If you dock on like a super big LLM and you didn't train it, or like you trained it, but you cannot, I mean, you would need to make the LLM itself explainable to then make the whole reinforcement learning structure explainable. I think that's the direction you're going with the question, right? especially if you reuse the latent text embeddings, right? I think there are some effects where maybe you can explain away certain impacts on the policy behavior, but yeah, I would err, maybe it makes it a bit more difficult.
I don't know, quite a few things I've seen in terms of people trying to make whatever policies explainable is, yes, you get a reasonably sounding explanation, but if it's a true explanation, that's a completely different question. And kind of how to bridge that to get kind of a true whatever, by whichever definition explanation, I think that's still a huge challenge.
So I think LLMs are nice to integrate in RL to add common sense. RL is really bad in understanding things that for humans are immediately possible to be understood. So explainability comes from common sense. I think it can add a layer of explainability. It will not solve the whole game, but this is reasonable. Nothing can really solve everything. But I don't see problems unless for some hallucinations or, you know, bad things that can happen, but we are here to try to make it work better. So I guess it can be an improvement over, yeah, not using it.
I'm not sure, but perhaps LLMs can be used there to look at your system and try to explain why that does one thing or another more efficiently than the human would do, so you can save human force. But it's just a guess.
So I agree that explainability in RL would be a bit more difficult because of this temporal credit assignment situation. But in general, like about your question about LLMs being helpful or not helpful, I'm not sure about LLMs explicitly, but if there are more progress in explainability ML, I would imagine that it could help in a way into RL research too. So that's what I would expect.
Thanks. I think there was a question here. Yeah.
Hi, I want to thank you first for sharing your thoughts today. And my question is about model-based RL. So what do you think the future of planning in RL is? Because right now we're of course learning in a value-based way, but I see increasingly more papers who try to learn the model as well, and then try to train in their own like imagined world model. For example, in some implementations of Dreamer, where they try to do one-step predictions and then roll those out to get like cheaper predictions about the future and the consequences of the actions of the model. So I was wondering if you have any insights into if this is going to be important, or if you think it's like just another heuristic we're going to use in the near future and then stop doing. So was that clear, or?
I didn't get the question.
So I think model-based RL definitely has a future, like model free. So I think they are kind of helping each other in some sense, because model free allows you to find more data, and model based allows you to use it to plan. What I think is that we should not try to model everything. I mean, this is kind of a known idea, but we should be really able to condense in a very small amount of information everything that is essential to learn the best policy. So you should apply a Occam razor philosophy, let's say, where you say, I want to learn the best policy I can, the best policy I need for this environment. The model-based approach should say which are the minimal set of information from this environment I need to obtain this policy. So I think if you are able to do that, and this requires generalization, feature extraction, and so on, then also planning will become easier, more feasible, and potentially also more accurate, because if you operate on a smaller set of features, you can also predict longer horizons. So I guess the future of model-based RL definitely is something that will still be investigated. And it will need, I think, to face the dimensionality of the problems we are trying to solve. So we need some compression and some ability to really condense in a small amount of information all the information that we need.
There's a few people that are currently pushing world models, model-based reinforcement learning quite a bit. So there's at least a lot of interest in that at the moment. Just to add to what Carlo was just saying, I think also there it's a question of figuring out what kind of priors, what kind of structures, what kind of regularity you can get in there to make sure that the model is as general as possible while not over-constraining it.
Yeah, I think the cool thing about word models, in addition to what was already mentioned, is also like it gives you like Jens just said, basically like really cool losses for the latent space, right? So you can basically constrain to your presentation learning algorithm already that, like, for example, it has to take into account predictability in the latent space, like all of these things, like contrastive losses. The other aspect maybe why, so we come a little bit back to like a past panel question actually, in terms of applicability, right? So if you have a new task and you want to solve it, model-free reinforcement learning often works relatively fine. But I think with model-based and word models especially, there's this idea that you train something more general, right? So like something which can be applied across a lot of tasks, and that's actually the argument, right, for the data efficiency, that, you know, you just need to relearn the reward function and you can basically use most components of the word model again to then continue the learning process. So there's like only a small amount of retraining necessary to do that. So it is data efficient in that case, so you can apply it to some systems, for example, a robot walking around, right? It makes sense to maybe train a word model for this one robot. Philosophically, also, I think the idea is basically that we as a human, right, we have some form of word model maybe in our brain if you look at it from a very high and abstract level, right? So not very scientific here, but like philosophically, right, we have the ability to plan into the future and we somewhat visualize in our brain what happens if we let go of a ball without actually, of course, really visualizing it maybe. So I think that direction makes it like really, really interesting as a research direction, right? So like trying to imitate the learning capabilities both on the reinforcement learning side and general prediction for humans.
Another thing is to understand how sensitive are your methods to model misspecification. So you can use one model, but perhaps the mistake of using the wrong model could be very harsh and lead to poor convergence. So yeah, that's another direction.
Yeah, I think model-based RL is very promising. So we're studying in offline settings, which we think that it improves sample efficiency. But if we are talking about the standard RL, then we can build better models. And there are already some research going on, like with this BeNeRL methods or like this model imagination and so on. So I think it's something that can be learned in addition and helps the learning of the policies or also planning.
Okay, more questions? Yep.
Thank you for your talks today. I was wondering a bit about the let's say, the discrepancy between RL theory and planning under uncertainty and experimental RL results or deep RL in general. Deep RL is moving very fast. We have seen a lot of nice applications today. We also see a lot of progress in RL theory and in planning, right? But it seems that these two are kind of racing and they're both moving into the same direction. Does it make sense that these fields are kind of more closer connected or working towards each other in some sense? Or is it natural that these are kind of like evolving independently? Do you have a vision on this? I'm curious what your thoughts are.
So the way I see it, I think they are a bit maybe not in the same direction. So because RL in theory, it's not yet scalable to be deployed in practice. I think that deep RL methods, they are more on approximation and they will with empirical tuning and so on. And there are different a bit research done on the theoretical RL on bandits or like in like simpler task and value iteration methods or something like that. So I would say it's a bit, maybe there is a bit of a gap between the two. That's my opinion.
Yeah, I also share this opinion that there's quite some gap. Also, I've noticed that the language that this like theoretical and more experimental RL speak, it's also quite different. Yeah, but recently, I think ICML 2 years ago, there was a workshop that was trying to join fundamental and more experimental RL, like also discussing like what is the different approach, maybe what kind of problems should tackle. But yeah, no one can stop, of course, like you can do experiments, but often, so both directions are important, of course, because with just a theory, it's kind of, like there is no like purpose. Sometimes studying just a theory, but if you study experiments and you don't know why some things works when some other are not working, then it's blind. But unfortunately, like yeah, there is a huge gap between those two.
Yeah, I would say this development is supernatural, right? So like we see it, like especially in robotics. If you go to a robotics conference, even between, like you would even think that within robotics we all talk with each other and we are aware of each other's research. But there are clear groups of people or researchers, like if you compare control versus learning, or like reinforcement learning versus like the best example is in co-design. Actually, like there is obviously evolutionary robotics. They have been at sort of like evolving robots now since the 1980s, I think. They hardly talk ever with us on the conference on robot learning or IROS and ICRA even, right? So they have their own conferences, actually their own niches. So I think like it's always needed. There are some people, like for example, robot learning, right? Is right between robotics and machine learning, or also reinforcement learning. These group of people who sort of like try to bridge the gap, right? So I think that's important. It's cool for us because we can basically take like the nice theoretical results and then try to maybe make them more applicable to like a wider range, because we often don't always care about provability or let's say our lower bounds, right? So like we care sometimes a bit more, okay, does it actually make the robot move and work in the lab, or what tricks, initialization methods, for example, what do we need to apply to actually get it to work? And then, of course, there are like the total engineers. So if you go to the machine learning conferences, sometimes it's like really only like a hunch, right? So how do they build up the networks to make them actually work? But of course, that's also motivated because there's industry, right? So industry is like really interested in applicable results. I think there's much more financial interest in that. So I think that's totally natural, but I think it's also exciting. Yeah, we need to talk a lot more with each other. That's why we have interdisciplinary workshops, right, where we all come together from the different fields of reinforcement learning. And this gives you like a lot more problems to basically solve, right? So like we pick the theoretical parts and try to combine it with the application problem.
I'd agree that there's quite a big gap in terms of how much is really directly applicable back and forth, but I don't think it's that bad. So even if we look at many of the more fundamental reinforcement learning approaches for which we have theoretical guarantees, how they are applied, that breaks all kind of assumptions for which the theoretical proofs hold, but they still work amazingly well. So for these kind of things, I would say there's still quite a lot of things crossing over from the more fundamental side, and we try it out in more complex problems, and that gives often quite some new interesting ideas on what to try, and then quite often it actually helps. And also the other way around, I hope that quite a lot of the more practical problems trickle back, probably in a simplified way, into interesting problems that can be solved on a more fundamental level.
So a lesson I learned during my PhD is that whenever you try to apply BeNeRL without having a solid ground on some theory, nothing works. At least in my experience, it was really something super difficult to make it work. I always found things to become a bit more usable when you have at least some ground to some theory, and then maybe you relax some assumption, you go towards more deep setting, but without going too much, let's say, far from what the theory says. So I think an important skill is understanding how far you can go from the theoretical perspective to the empirical one, how much you can break the assumptions of the theory, and also some, tricks to make the whole empirical setup work. So I think theory should always be in mind and the starting point of everything, and then you can develop your methods based on that.
Thank you. I think you all raised some important points about how different fields have to communicate and start that conversation, which can be quite difficult to do, and that resonates quite a bit. Any other questions? We have a bit of time left.
I think at least one good question.
Yeah. Now is your chance to ask a good question.
No pressure.
Yeah.
Do you think there are any problems in reinforcement learning, or at least problems that you think is significant? And this could be because you are particularly invested in a particular subfield that you think is within reach or be close to a breakthrough in let's say, the next 10 years, 20 years or so.
You mean problems in terms of applications or problems in the methodology?
It could be theory or application, just any, in the whichever domain that you are invested in. Do you think there's, I don't want to say holy grail because that's too big of a word, but something maybe like a personal holy grail, so to speak, that you think is something I really care about and I think I can accomplish it within the time I have?
Okay, so in my research I focus mostly on generalization, which I think it's an important problem of RL. But I think maybe also more important problem, it's exploration that remains really the most important one, I think, because if you find good data, you can learn. So I think we still lack solid exploration strategies, and sometimes we still rely on stochasticity, hoping that something meaningful is found. I think we need to incorporate some kind of self-understanding in the model of what the model knows, and starting from that, add some kind of active exploration layer to make the model able to understand what it's still lacking and to seek for this information to increase the knowledge. So we need, I think, in the next years, it will be nice to see progress in this direction.
For me, one of the big problems in reinforcement learning always has been the reward design. So how you define a good reward function, and then like if you design a reward function, you see what the agent does and does some reward hacking, and need to go back and start refining your reward function and be careful not to over-constrain it and whatever. So that, at least for me, always has been a tedious and somewhat manual process. I would hope that with the kind of common sense reasoning you have now in foundation models and LLMs, that hopefully can at least to a good extent be automated to catch these kind of things and refine the reward function to really get what you truly wanted and not what just happens to fulfill the reward function.
Yeah, in terms of reinforcement learning, I would say maybe if we take on the application field of robotics, I think we will probably see in the next 10 years, right? So if we extrapolate now over 10 years, probably seeing robots learning some, or like applying some limited version of reinforcement learning actually in real environments indoors, I would say, maybe outdoors. So I think reinforcement learning will find its way more and more into applications or like into home appliances, maybe in the form of robots, maybe also not. Yeah, I think the best example, or like which gives me basically a bit hope for that, is like, for example, Boston Dynamics. Everyone probably knows that company. They have been really good at control, and now they're also figuring out actually that, hey, reinforcement learning works really well. So they have been pushing actually a learned policy to these four-legged robots. I forgot the name now. The spot robot, yeah, exactly. The spot robot actually in the industry. So some spot robots who are actually now running around on industry areas, they actually are powered by reinforcement learning, but they don't do reinforcement learning themselves. So I think we will see probably some more applications of actually in real world online adaptation to environments. I would hope.
Something connected to the very first question about open problems. It's also till large scale reinforcement learning for me in online setting especially. And then, yeah, as I said, there are quite some ways and models to state it, like how you model the reward function, how you model the transition function there. And then how to provide the formal guarantees for the large state spaces. So currently there are just, most of the results are for linear models, and then there is a big question, how do we extend beyond the linear models?
So if we are talking about general RL, yeah, I would say like the exploration and apart from the reward shaping that you talked about, also the sparsity of the reward, lack of like suitable feedback. And yeah, there are sample inefficiency. I would say also like scalability, like because of the whole, like RL methods take longer than any other methods usually to train. And yeah, some practicality of deployment of reinforcement learning, like catastrophic forgetting or some other things that we need to think about in deploying RL methods. But yeah, then if you go specific to different directions, then everyone has their own open problems, I would say.
Okay, so then I have one last small question, rapid fire, just a bit of a joke. But which one, if any, is your favorite LLM you use every day? Could be Gemini, GPT, Claude, or anything else if you prefer. We do a little stuff.
If you're worried, what? That is.
Which one is your favorite LLM that if you use it, you know,
yeah, I only tried ChatGPT, so I don't know about others, but I heard Claude is good. Yeah.
So far I was using ChatGPT, but I went to maternity leave on November and came back on in May, and now everyone is using Claude. So it's yeah, maybe I should look into it.
Claude Fable could be good for children, right?
Still need to learn.
Well, I have to be honest, I have a Google subscription, so I'm just using Gemini, but it's like, I didn't really, like, I just use it sometimes for some small things, so it's good enough most of the time.
Similar to Kevin, my university has a Copilot subscription that also complies with the whatever, what's it called, kind of security things and privacy things. So yeah, that's my default.
So my students are very happy with Codex, which I guess it works very well. I use mostly Gemini. I will be happy to have more time to spend on coding and running experiments. But for me, Gemini is the most useful one to, you know, some writing some nice English text for whatever reason, doing some nice figures and so on. So for now, I didn't really spend too much time coding. I hope I will be able to do it in the future. And I guess Codex, as far as I heard, it's now the best tool that you can use. Also, Claude Code is not bad, but I think Codex has a slight edge on Claude.
Thank you again very much for coming, presenting, and subjecting yourself to 50 minutes of funnel discussion. So a round of applause for our speakers. Okay, so now we had one or two slides to finish. It works now?
I think so.
Okay.
Nice.
So thank you so much. It's really literally just one slide with some photos, and then we explain the rest. Okay.
And this started working just now, like at this second. So we're very happy about that. Shall I start? Yeah. So we would like to thank all the participants for being with us today, throughout the day. I think we can all agree that we had a fantastic time, a series of great talks. I met many interesting people as well. I hope you did too. And now we close with some 1 minute reflection on how the day went. And finally we go for drinks. So here are just some pictures we took throughout the day, and there are many more. We also had the professional recording that was happening this whole time. So documentation is around, and you can see that hopefully everybody enjoyed, and I think the snacks and the food were also really good. So thanks, Giacomo, for taking care of the catering. It was everything you promised. So, anything you would like to say?
Yes, so we are gonna post the video online soon. So the link used for streaming that is on the website will already include the full recording of the day immediately. But if I think it will be like a workshop I did 2 years ago, MindLabs will also do a cutout of the recording, removing all the pauses, so there are only talks left. So that may take a bit longer, but I think in 1 or 2 weeks maximum we should have it, and we're gonna advertise it. For the rest, we close the event here. We do have some hour and a half of reception with drinks and more food again. So we do have some platters of, I just saw them behind that, actually there's a lot of food, with both meat-based and vegan options. So just grab a drink, eat, and enjoy the networking session. The only thing I would ask is if everybody can go to the drinks or at least leave the chairs, because our fantastic student assistants will very quickly remove everything and clear up the room, so we have all more space. Okay. That's it.
And maybe at this point we should also all thank the organizers for organizing this awesome workshop.
And the volunteers, guys, behind the scenes working very hard.
Have fun with the drinks.